Hey everybody, how are you doing? That's Brian on the piano. Thank you, Connor. Connor, 20 points. Brennan, I hope we'll get to see campus again. I think we will. I know it's such a beautiful. I got some gug gig. It's dig dug. I don't know how to say it backwards, but I do play piano. But that's not me on the piano right there. And I gave away my piano recently. I had a piano up here in my apartment and gave it away. Because everyone, Mila, Alexa, Corbin, Nicholas, 20 points, Sylvia, Brad, Ben, everyone I can see on the screen, 20 points. Say hey on the screen for 20 points now. So everyone was already saying hey, but go in, jump in. Good morning, everybody. How are we doing? Hopefully everyone can hear me. Yes, I do a lot of these things at the start of class just to make sure people can hear me. Lest people are like, it's like happened once or twice. We've had the weird tech issues every once in a while, but, we need some Mega Man to start out. Some classic right here. Just get going, get your Rebel out, get your coffee. There we go. We are good to go. So with that in mind, I sent out, who saw the image I sent out yesterday? Did anyone go and look at, we got to hop over to the main screen now. Did anybody, what? Click the button again. I don't know what's going on. The world is weird, and things sometimes don't work the way you expect them to. So, let me log into Canvas right here. I was not logged into Canvas. And let me log in. Security Duo security. Gonna click the phone button. So what I sent out yesterday was an image that shows you how to know to check the conditions. And especially, I keep talking about written tests, but I can't do written tests. I like my written tests. And so when we have a written test, I'm very, very specific on what students have to write down. So you might lose points on the homework. You need to talk to the grader and tell them to be a little tougher on these questions when you have to check assumptions. So when you're checking your assumptions for the model, here's the steps you'll take that we were going over yesterday. Now, I want to talk about this right here, because I really wished I could just put in the image of me going like this, like, I don't know, like it all depends what you do right there. Like it's up to you. This choice right here, if you get down to this, is like, I don't know, you decide, because there's statistics is kind of I love it for this reason. It's not exact in what you have to do. Like you could toss models for other reasons. You could throw them away. But this right here is like where a lot of people are going to differ. And what does it mean? Are the problems small? What does small mean? Well, it's up to you to decide if the problems are small. So let's start here at the very top. Now, do you want your p-values to be above 0.05 or below 0.05 when checking assumptions? 20 points, right answers in the chat. When you check assumptions, do you want your p-values to be above 0.05 or below 0.05? Checking assumptions. Boom, right there. People, yes. If you remember from yesterday, that was a big thing that I kept saying. Yep. And this is only for assumptions. Only for assumptions. Only for assumptions. We can't make that clear enough. People are like, you want high p-values? I thought you want your p-values low so you can reject the null. But if you remember, all the null hypotheses were things like the linearity is good, the equal spread is good, the normality of the residuals is good. You should know all three of those. You should try to memorize the three conditions or the three assumptions, which we assume that a line well describes it. First assumption was linearity. Second assumption was equal spread, that the points have an equal spread around the line. And then the third assumption is that the points are well described by a normal curve. The residuals are well described by a normal at all individual points of the x's. So try to put those down from your notes, three assumptions, and you want all the p-values to be above 0.05 because the null is linearity is good. The null is equal spread is good. The null is normality of residuals is good. So if you reject that, you're saying it's bad. You're saying I have evidence it's bad. So you want them all to be above 0.05. If it's yes, you're good. You're done. That's it. So then we get to, is the sample size greater than 25? Like if you fail. So this is when you fail this way. This is when you say no to a condition. So if you do not meet this condition or you do not meet this check right here, you would go right here. Oh, Streamlabs, it did change color. Oh, Streamlabs, you look so cool. That's like I saw that in the thing. Whoa, I like that. So everyone's saying the points out. Great job on the points on everyone. I thought they were tied. Oh, did it do it twice? Streamlabs. You only have to do it once, Streamlabs. You're totally cool, but Um, let's see. Okay, I don't know why I did it twice for the first one. That's so weird. So we see right here that is the sample size greater than 25. This is not like you pass. It's one of my pet peeves. People sometimes say like, I passed the condition of my sample size being greater than 25. You just get to continue on. So you don't. Stream is being odd today, but hey, that's fine. It's still working. Right here, we would say we continue on, but if your sample size is small, it's over. But what do you do next after you? So who's got this 100 points right here? Get up to 200 points today on these Thinking Thursdays. What do you do if you have a large enough sample size and if you have a bad p-value, low p-value, what do you do if you have a low p-value and your sample size is high enough? What do you do next? Who knows? I should have never told Streamlabs it was doing a good job. It's working double time now. Look at the plots. Mila right there, 100 points. You're totally right. Look at the plots. So if you see the path we're following, you're going to look at the plots, and there's 3 plots. So, we can pull up those 3 plots right here. Let's see, 20 points, everyone else. Mila, 100 points. Amazing job, Mila, right there. We're going to look at the plots. We're going to open up R, and I posted, I think, the file for you guys yesterday. There's some hints for your homework in the file, and we'll be talking about the last few homework questions here today also. So let's go here to BAS 320. So many files. I posted this one from you. Look at that. Okay. So when we make the model right here, we made a model right there. Sure. Here's our model. And Okay. So there's the check regression. And I think about the types of questions I can ask. Pretty easy on the test. These would be nice and easy questions. Let's say I put this picture on the test. And I say the first plot checks which of these conditions. So I want you to type 1, 2, or 3. Ready? Here, don't type in the chat real quick yet. Because you don't know what 1, 2, and 3 are yet. So 1 is linearity. 2 is equal spread. And 3 is normality of residuals. And while you can, which of those are best checked via plot right here? Which of these are best checked via this plot? Or it could be 1, it could be none, it could be all of them. So which of these are best checked via this plot right here? No one's got the right answer yet. 100 points right answer. The answers aren't technically wrong yet. The answers aren't technically wrong. No one's got the right answer yet. 100 points right answer. No one's got the right answer yet. Boom, Henry. Henry is right. Henry's right. Henry and Corbin, they got it basically at the same time. 100 points, Henry and Corbin, you're right. This is the line right here, and the line doesn't go through the center of the data. It kind of dips at the end. This is what Brad was talking about yesterday. Brad said, if you take the line and make it flat, do you see how we have right here behind my head, just look right at my head, that you have the points going below the red line? And then if you look right here, the points are going below. This area right here is this area right here above my head. Does everyone see the connection between the points here and the points that are right here? So the red line, that red line right there is this black line right there. I wish it was a red line. That'd be nice, but I got the red line reserved for this. Now that's the linearity condition, which was the first thing I mentioned. And then the equal spread is seen by the points like having an equal spread around it. Like, is it the same thickness throughout here? Now you ready? What does this graphic check? 1 for linearity, 2 for equal spread, 3 for normality. First person, 100 points. Boom, Mila, 100 points right there. Boom. Let's give it to one person, right? Brennan right there. Yes, nice. It's number 3. Yep. This checks the normality of residuals. I don't think it's the best. Hint, hint, hint for the next question. But this also checks, well, this, hint, hint, hint. This checks normality of residuals right here. It's a histogram looking at your residuals. If you look right there, it's residuals. I have to vanish. So this checks residuals right here and just looks at, do they fit under a normal curve? Not the not the best right here. Not the best graphic. Emily, 100 points, cracking me up right there. Not the best graphic. Now, what does this, I want you to say it checks this. You have to say it checks, so I know you're responding to this question. 100 points first person. What does this graphic check? What does this graphic check? You have to say it checks this. It checks. What does this graphic check? This is where people get tricked. Boom, Casey. right there, 100 points. And Emily, yes, it checks 3. And Corbin, it's going to check the normality of the residuals. This only checks the normality of the residuals. So you have condition 1 and 2 right here with this one with linearity and equal spread. And then this one is normality of residuals, and this is normality of residuals. So I know it sounds crazy, but your last 2 plots are both just the normality of the residuals. Here's a normal curve right here, so that indicates normality. And then values of residuals if normal. So it's kind of giving you a tip right here. So that's normality. And that is a normal curve right there. It's a normal curve plotted on top of the residuals. You don't see any sort of normal curve stuff over here. Someone could say, well, you could check the normality of the residuals by seeing if a normal curve fits the residual. I'd be like, I can't visually inspect it that well. This one has problems with the normality. And once again, you want to use this plot right here. The issues with normality of residuals are seen right here and slightly right there. The further, like this is, I'm not worried about this. Like that's not perfect. The further it is away from this red line down the center, that red line down the center of this is the perfect normal, which is this. And you'll notice where there are the problems down here, and that's the problems here. You really want to look at this graphic though, because it's there. Would equal spread be measured by the scatter as long as it's, yeah, so let me show you, I'm going to graph equal spread better. We don't want it that tiny. Ah, there you go. So the equal spread, I'm kidding. So let me do this. Let me get it to a decent sized graphic. I'm going to make it bigger than that. That's good. I like that. And I'll show you what we're going to do to talk about equal spread real quick. Okay. I can return now. I didn't snap off. There we go. Okay. So to do equal spread, what exactly is going on right here? The equal spread, when you think about equal spread being passed, what it means is at all points we have the same sort of spread around the plot. And there might be some sort of lack of equal spread. I mean, do you include all the outliers? Because these are more outliers right here. So these are going to hurt normality a little bit more. So maybe the equal spread is a little bigger there. The equal spread does look to be not so good here. So does everyone see how I'm kind of looking at equal spread? I'm kind of excluding outliers because I'm looking at the general spread of the points, and there seems to be an outlier issue here. There seems to be equal spread. There also seems to be a linearity condition. So what I have in the red is equal spread. So the red is showing equal spread. The highlighted points are showing outliers, which will probably hurt the normality of the residuals. So you can view a little bit of it there, but this is not the best graph for this. And then what I'm drawing right here is the linearity. So there does seem to be a problem with the linearity of the model, which it's not well described by the line going through the middle. So I've drawn on top of this, which is what I used to have to do when we would do these things, but now we just usually just run it inside of R. I mean, you could get R to draw this, I guess, if you want. I should do that. I know how to do it because there's a really quick command in R you can do called choose order, which I believe we'll see today. This function right here in R called choose order. So we're going to do choose order on M, and it'll show you if there's a linear bend through your model. I mean, a polynomial bend. It'll show you if the linear model is not appropriate. It'll do a polynomial bend through your model. So you can see if a higher order polynomial has a better fit through your model, and it's that quick. So I could plot I could do a thing that plots the polynomials and puts them on like dashed lines and uses like a lighter color. But you can see here that bend I'm showing at the end that I go off screen to point at, that there's an issue with that there's some sort of bend through the model. And we're going to see that show up in the p-value especially. Here's the p-value for the linearity. The p-value for the linearity is low. Actually, all of these are low. We fail every single condition. Now, who has a strong opinion about this? Toss this model out or keep this model? What do you say? First person, 100 points. Toss it or keep it? Toss, 100 points, Brian, right there. Anyone else? Toss it, Ryan, 100 points. All right. Megan, Mila. Okay, here we go. I might toss it. If I were to toss it, I'd probably go to like a second order polynomial model. More on that in a bit. But what are your reasons for tossing it? What's your strongest reason for tossing it? And I kind of gave it away. What's your strongest reason for tossing it? I literally kind of gave away what I'm thinking by saying what I'm going to do. What's your reason for tossing it? 100 points. Who's got it? Poor linearity, Brennan, exactly. This is what you'd want to mention if you're going to say why you're not using the model. You would say it failed all the conditions. It's got, you know, the normality is probably most impacted by the outliers. Like these outliers right here are really strong that are impacting the normality. That's the point down here. This point right here is that same point right there. Like in this graphic, it's this point, and in this graphic, it's this point. So it's showing up in these spots and it's hurting our normality. But the linearity is probably my biggest concern. So you can do transformations on it. You know what you could do? Can we do suggest transformations in this? Well, you can square it. Let's just go here to weight and do square of weight. And now we've got weight squared in the model. Or let's do this. Let's go survey. This is exactly what we're going to be talking about today. I'm going to go squared, and I'm going to go here. This is very much today's topic. I'm going to go to weight squared. So now I've literally stored, please take a look at the code. This is very important for today's lecture. I've taken weight and I've squared it. Does that make sense that I squared people's weights and I just stored the squares of their weights? Does that make perfect sense? I squared a variable and then I wrote it into the data frame right here. If you remember how you can write to a data frame, you just call a position that exists. A lot of times we call this like transformed X. You could do that, transformed weight. You can call whatever you want. The notes go through some ways of storing it. Computer, behave. And we do this. And, oh, no. That was a very bad idea. I can fix it, though, like that. If you saw what I just did, I just overwrote the variable with a squared version of it, and I don't want to do that. So now, there is a difference, actually, between what I'm doing here. No, is there? Yeah, because the model I created would carry through model hierarchy. More on that on multiple regression. So now I don't think we can visualize this. We can? Did I store my squared weight? Let me see if it's running squared on it. Or did that not fix the problems? Let me look at my summary of the model. Make sure I've got my squared variable in here. And it does look like I have different coefficients. And then let's look at the check regression on the model. And it actually kind of looks worse. I think I need both in here. So I might need weight. And now it should not visualize. Let's look at the summary. Both my coefficients are in here. And look, this is kind of a peek into multiple regression. What do you notice about the p-value for weight squared? The p-value, I don't really get why we are making transformations, because it adds new information, because it fits the model better, and why we can make them. Oh, Sylvia, great question. Sylvia, you're on 200 points. Amazing question to ask. The point is because there's unexplained variation, and you can see it right here where our model's not going through it. So when you look for transformations like a polynomial transformation, which I'm doing right now, you might say something like, if you look at order 2, the red line, do you see how the red line kind of fits through the model better? It kind of goes through the data. You're trying to make your model go through the data. So you're trying to add, like you're trying to make a mathematical equation. Just think about it as math, which I know everyone loves math. But you're trying to write a mathematical equation that goes through the data. And the mathematical equation is going to be based on variables you collected. So you're just trying to figure out some math equation. And then you're like, well, what if we do this with our variables? What if we square our variables? What if we square root our variables? What if we take the log of our variables? What if we do this to our variables? Can then we come up with some equation that uses it this way? And that way someone could tell us their weight. The whole goal is someone tells us their weight, and then we tell that person their what? Somebody tells us their weight, and then we could really make a good guess at that person's what? Who knows 100 points? Someone tells us their weight, and we can make a really good guess at their what? Their height. Exactly. And that's the whole goal of this, is to then, be like, well, what if I were to square their weight and then times it by 0.25? So the coefficient right here, this coefficient is when someone gives us their weight, we're going to square their weight, and then we are going to multiply it by negative 0.0004692. So if you were to write this out, which this is a really good example, especially for today's homework, not today's, what was it due? Tomorrow, I think it's due tomorrow. So let's bring this up in the background right here. Let me do this. I think I can do it this way and it'll look pretty good. Let's put this here and let's zoom out a bit. Okay, so I'm going to try to write on this and so everyone can see and I can write the equation. Do you only have to transform one variable or it depends. And one of the goals is we always want y untransformed. So that's a big thing for tonight's home or tomorrow night's homework, I believe. You want to untransform the y. This is fine right here because I'm predicting height. I have height equals 42.7. I'm going to round that. Plus weight. Oops, well, no, let's not put weight first. Let's put weight second. And then here, I'm bumping into my mic. I don't need the standard errors. Plus 0.23 times weight. I'm just going to put weight right here as a W. I'd write it out. Do I have enough room? I'm going to run out of room. Minus, oh my gosh, this one's so 0.004 weight squared. And you put the squared up there. Does this, we wouldn't be mad with it due tomorrow, though. Is it due tonight? Yeah, I think we're fine to put it due tomorrow. I think there's one due this. I think multiples coming up here. You guys want it due tomorrow night? Due tomorrow night? Is that the vote? Take a vote right now. I know it's going to win. Let's do it. Let's change it. Unless all of a sudden there's a resounding, like, keep it, dude. Yeah. Unless all of a sudden there's a resounding. I think you guys might have even heard Echo Brian. Let's go here. Assignments. Simple linear regression. Then we have, so that this is due, is that due Saturday? Is that due Saturday? If today's Thursday, Friday, Saturday. Oh, wait. Oh, today's 18th. My gosh. Do you ever have where you just like, you don't know what day it is? That's the way quarantine is, right? I don't know what day it is. I look and I'm like, is it the 18th? How is that possible? Every day since Corona, exactly. Also, there's 2 midterms listed on my canvas. One says it's 2. There's a practice. Oh, maybe there's only 1 quiz. So let me look at your guys' assignments real quick. Make sure it's not too confusing. Because I will be sending out people reminders here after class. This is the only one right here. There should be midterm requires respondus. And then I just think there's the grade one right here. So let's make this go away because I don't think that'll harm anything. Once there's respondus though. Yeah, I'm going to keep it the way it is because people have been doing it. Just make sure everyone in class should know, do the respondus one. Grades are looking pretty good. I think they're high 70s right now. Grades are pretty good so far. Grades are pretty good. So congratulations. Keep taking it. If you make it a little bit lower, then don't worry because more people are going to be taking it. So maybe grades will go up. Maybe they'll go down. Who knows what happens? How long do we have for the respondus? 2 hours. So it's more than enough time. You have like 4 minutes per question. Allowed to ask how many people have taken it so far. I think like a third of the class or a little under half. So we've got a pretty good estimate of how it's happened. Like good enough that I have a decent understanding, but it might be, the people who take it later are more likely to do this. That seems like survey bias. Those who, yeah, exactly. Brad, 100%, 100 points, Brad, right there. Yep, totally right. There's a time order to it. I mean, but at least I know it's not destroying people. Like if the first people who took it absolutely failed it, then I'd be like, uh-oh, oops, there's going to be a big curve on this. I don't expect much of a curve. You do get your grade back right away. You don't get to see the answers till like the weekend. That way, if there's any issues, please take it while the time frame is up because there will be a penalty if you don't, because it wouldn't be fair for somebody to take it like Friday, Saturday, Sunday, because they'd have more time to study. They could ask people. Don't ask people. Don't post things. Don't say, here's the questions, because that's not the goal of it. There we go. Any other last questions about that? We're going to hop into the notes right here. Let's hop back to the note. We are back to the notes. Back. And their last questions. So many notes. These are all the conditions. And these are all the tests. And here is where we ended. When we email you for class points, do you manually add them? Yep, I manually add them in. I go and I click everyone's names and I take and I add the points. Yep. I probably need to make a better way. I've had some better ways, but I have to go and manually add them. I like giving you guys points. Like, I like that you guys can be here live and get points. Lots of people have tons of live points, and I maybe need to adjust the scales and everything, but I have so much fun giving away points. Like, I like giving away the 1,000. If you guys can't tell, I really like that. I'm like, you'll see me. If you ever see me look up, that's when I'm like, I want to give away some big points. I'll like do this, and I'll be like, okay. And I'll be like, big points. It's just fun. It's like a game show to me. So hopefully you guys enjoy it. So here we go. Let's take a look at this graphic right here, but not the graphic first. This is something we should know instantaneously. If you're in class, this is an easy 100 on the test. Are we good or bad on these p-values? Yep, the points I give you in class. You email me. Yep. I haven't been emailing. No, just try to email about reports. You can send out a spreadsheet template for people to fill out with their points. Yeah, I could do. Yeah, I could be like, I could do that. That's a good idea. This is all very, very good. This is all very, very good. Remember, please make sure to remember throughout the remainder of the class, BAS 320 initials. Oh my gosh, I cannot spell. Title here. Yep. Because I have to enter them afterwards. If I had a TA watching, they could like give away points, but I can't. I've tried one time like manually doing it while I'm teaching, but it really slows it down because I have to be like, yeah, so make sure to email me those points. And so right here, we have, they're all good p-values. Exactly. Great job. So we don't even have to look at these plots. I mean, you could be like, oh, they all look good, but you confirmed that by the p-values. The p-values are your first line of defense to see if the models are good. This next one right here, look at the p-values. How do they look? Good or bad? Good or bad? These are horrible. These are ridiculous p-values. They're horrible. Everything fails. What is maybe the worst condition here? It's a fight for the worst. There's only two conditions here what is the fight for the worst? We did this yesterday, but still good review. What are the fight for the worst conditions? There's two that are really, really just trying to be the worst. And yep, so, wait a minute. Let's see, I want to keep looking at the answers. Put down the two that are fighting for the worst conditions. Well, if you're saying 1 and 3, let me think which is the order of them. If you're doing them in order I did, it wouldn't be 1 and 3. And plot 2 and 3 check the same thing. Ooh, I'm seeing. So you get 100 points if you said normality and spread. Normality and spread. Because the spread, look at this right here. Do you see how tiny the spread is here and the spread just goes crazy? Does everyone see the spread right there going crazy? Does that make sense? The spread right here starts tiny, bigger, and it goes crazy. And then does everyone see over here the normality is way off? So the normality is the red line going through the center, but a lot of people think that this is a linearity. This is not linearity. It's if it follows this normal curve. And look at this crazy peak right here. So you don't, this graphic, don't look at that graphic. Look at this graphic right here. These two things are doing the same thing. I need to tell Dr. Petrie. I actually went in and removed it one day. So you can remove it if you edit the function, which is not too hard to do. You find where it's doing the histogram, you just remove it out. And but this is the one you want to look at right here. And look at how far it breaks away. We've got a big problem here. We've got a minor problem down here, but this big problem up here is enough. So there's really outlier issues which are causing the issues, and there's a humongous skew to this, which is showing up right here. So the normality of the residuals is really bad, really bad. This is a toss-out model. Regression's not appropriate. So what does it mean when you toss the model? You're saying that your model is not a good reflection of like what you're trying to model. It's not going to make good predictions. It's not going to make consistent predictions. So we don't want that. I did skip one step last time. Let's do the steps in order. It's in the flow chart. Step 1, do what? You guys got to tell me step 1 of the flow chart. Be looking at your flow chart if not. And what's step 1? What is step 1? First thing we do is we look at those p-values. Alex right there, 100 points, and Sylvia. So we look at those p-values. Grant also. So we're going to look at the p-values first. Remember, look at the p-values. Now, what is your choice? Great job, Emily. 100 points right there, Emily. What is your choice right here with looking at the p-values. What is your choice with looking at the p-values? Look at those p-values, like you're doing the assumptions, and what do you think? What do you... Above 0.05 is great, below is bad. 100 points are there, Alex. And then, so what would you write if you had to write like a sentence about these p-values? Write a sentence right now. Try writing a sentence to explain to someone what you found out by looking at these p-values. It could be summed up very quickly. Let's see what people say. Try to interpret those p-values and what they mean for these tests. And these are tests to see if our regression is like a good regression. So what would we decide? This is the tough part, especially the written parts on the test. This is where I see people completely stumped. And they're like, what do you want me to interpret about these p-values? I'm like, what does it mean for the person who's trying to use the model? If we're trying to use this model, what does it mean? And the answers are kind of below it, but let's see. 1,000 points first person whose answer is great. Let's see. I mean it. Let's see who's got it. Sylvia right there. That's it. Perfect, yeah. And don't worry, that's exactly what I wanted to see. It passed every test but the normality. Exactly it, Sylvia. Great job, Sylvia. Passes everything but the normality. Now, what is step 2? Step 2 I didn't do last time. Sorry about that. But, and so make sure definitely with the pass, Brad, make sure to say it passes these up here and then it didn't pass the normality. Like, it is true that normality is statistically significant, but that means, and Alex definitely, yep. Next, after we fail a test, we see if the sample size is at least 25, because then we can continue. So if the sample size is at least 25, we can continue on to go and do what? Sample size is at least 25. Now what do we do? What do we do next in our flow chart? Sample size was at least 25. We do what? Since it's at least 25 and greater than 25. Yeah. Don't worry. I'll never put exactly 25. And it's not like 25 is a magic number. I'll never do exactly 25. Like someone could have written it so it was 20, but don't worry. It'll never be exactly. So we go back and look at the plots. And the one that it failed on was the normality of the residuals, which is going to show up right here. And it's due to outliers, it looks like. It looks like we mainly fail due to these points. As everyone see, if you were to trace over these points, there's the point. This point is that point, which is that point right here. This is the extreme outlier we are noticing throughout the plots. It's the extremely high, thus it has an extremely high residual because it has a very big residual, and thus it's way off where we would expect it to be. It does not follow the normal. We shouldn't get points over here. So, do we toss it out? One outlier can have an extreme impact. One outlier, 244 is not so bad. This is kind of the, do I still have it up? This is kind of the, this is the I don't know zone. I mean, it's personal preference. It's pretty bad. It's pretty bad. I don't know. Tough one. Not a great test question. This one right here, well, let's look at the p-values. All the p-values fail. So now you're going to look to see if your sample size is greater than 25. Sample size greater than 25. The big problems here, where's your real concerns on this one? Where's your big concerns? What's your biggest concern on this one? What's your biggest concern? Think through your 3 steps, your linearity, your equal spread, your normality. 100 points. What's your biggest concern? It was a big concern for this one. I need to put it back down to 20 so people are like a normality. Silly. Great job. You got this down. Brad also. I see the more concerns right here. The linearity looks to be fine because the linearity is this line looks to cut through the middle. That line looks to go through the middle. Equal spread, not so bad. I mean, this right here is just an outlier, which the outlier is going to be showing up down here. So I'm more concerned with this. Here we go. Do you guys like these questions? I love these questions. I think they're pretty easy to know the steps. And once you get it down, you go through the plots. You're like, okay, look at the p-values. If p-values are low, there's a problem. Look at my sample size. If I can continue, go back and look at the plots and examine them visually to understand what's going on. If you understand the steps, you understand how to read the graphics, not so bad. It's just like reading a book to me now. But you have to practice it. You have to be like, okay, let me look at, we got practice slides right here that go through the steps so you can see how to do it. Really good review of that concept. Who feels like they got this down? Let's see some thumbs up in the chat. So let's see some yeses in the chat or no's. If there's like no, I'll do like 3 more example or another example. But how do people feel about knowing the steps? You got it down? Yes. So that is how we check the conditions. You know what's really good about this though? Check this out. When we do multiple regression, and this is what I love, simple regression is maybe one of the hardest chapters in this class. But when you do multiple regression, which this is now a multiple regression, watch this. I'm going to make my multiple regression. I'm going to check it. Guess what? This is the output for the multiple regression. Great job in the chat. So as everyone see right here, this is now has multiple linearity conditions to see if the fit for the x is good, and we still get equal spread, and we still get a p-value. It doesn't matter how big I make this multiple regression, because I could go crazy right here and make a ridiculous multiple regression. And guess what? When I check it, look at this now. When I check the multiple regression, we still just get p-values for all the linearity conditions, and then we get our equal spread, and we get our normality. So all in a multiple regression, all you get is just more tests for linearity for all of your x's. Every x gets it, and you get a p-value for your whole model. Which, wait a minute, do you remember when we just did 1x? When we did 1x, we got, oh, it's made about the plot. When we did 1x, we got a p-value for our x and the overall model. Now, one thing I do want to point out is when you have 1x in your model, the p-value for your x right here is the same as your p-value for your model, because your x is your model. There's only 1x. So if you look at the p-values, which I wish we had a good one, here's a good one. When you look at your p-value right here, this p-value for your 1x is the p-value for your linearity of the model, because your x is your model. There's only 1x. So if the x is linear, your model passes the linearity. But when you have multiple x's, you get what does the non-enough duplicate rows? Oh, great question. So the way in which it does these tests, which the theory is explained a bit. Don't worry, I won't put down the test. Sylvia, you got 1,000 points. You're asking some amazing questions today. Did I already give you 1,000? If I did, you got 500 on top of it. So you had ridiculous points. I love the question. The way duplicates work is to test some of the conditions. It needs duplicates, or sometimes called replicates. I'll draw visually what they look like. The way a duplicate looks like, and this will not be on the test, but it's a really good question because you just have to know how to interpret them. You don't have to know how to theoretically get these. When you do the test, it needs duplicates at the same x to see if the line is going through it. So if we don't have any duplicates, your model might look something like this right here. This would come back with not enough duplicates, because there's no repeated values of the x, so you can only visually inspect it. This test can't run because there's no duplicates, but you could have a model like this, and does everyone see how now I have duplicated values of the x? And what do I mean? I mean at a value of an x, there's duplicate x's. So now, and those are meant to be on top of each other, like they're vertically on top of each other. So duplicates allow us to compute these. So it's just saying there's duplicated values of x's, and if there's not enough, it just can't run the test. So it'll give an NA because it literally just can't compute it. And that doesn't mean it fails the test if it gives an NA. It just means can't compute, no value. And so I think one of them must set it. Maybe it was on the past one when I I think it was on, great job, quick eyes on that if you saw where it said not enough duplicates. Right here. So here we go. They're not doing it. Categorical, only 2 levels, not enough duplicates, overall model. So when it says not enough duplicates on the overall model, that would mean you need x's that have all the same values, and there's just not enough duplicates, and it can't do it for the categorical. So it's not going to do it for a categorical, which you can do regression with those, with indicator variables. More on that in multiple. So really great questions right there. Let's hop back to the slide deck. Okay. We got the linearity, all this good stuff, and now let's fix a regression with a transformation. Now, what is the goal of a transformation? The goal of a transformation is to make the x linear, to make some sort of linear relationship between x and y. So we have a lot of times that we have these transformations we use, which are often log or exponent or natural log or squaring it, whatever we want to do. And what is the whole goal of this? To make a model that is appropriate. Sometimes we get models that are inappropriate, and we want to fix it with a transformation. So the whole goal of this is to make a better model. So let's take a look. We've got right here where we have distance, and we could take the log 10 of distance. We could take the square root of spend. And I totally remember the function now. It's just find transformation. So we'll see it here in a moment with the find transformation function. But look at this data. Look at this data. If it were to go swooping down this way and swooping back up, it would kind of look like a what? If it were to go swooping here, it would kind of look like a what? Who knows? You know this shape. Everyone knows this shape. 100 points. Found along. Know this shape. I'm just going to keep making it until someone says it. And you know it. It's not a line, though. Parabola right there. You're right. Sylvia, 1,600 points. Keep getting those points. Parabola, James right there, and Emily. So 100 points for both of you right there. And so right here, it's a parabola. It's a parabola. But maybe it is, maybe it isn't. We're going to do this. So you might say, well, why are we taking our values and raising them to this value? I'll show you why. Because we've got a function. The function we have, which we'll be seeing here through the notes, is called find transformation. So find transformations is this function here, and it takes your original model. Let's look at the original model. So here's your original model, and it finds the highest r squared, which means the most amount of variation in this y is explained with this x. And apparently I need to take height and raise height to the third power, and I need to take weight and raise weight to the negative 0.5 power. So how am I going to do this? Does everyone see how this was chosen? This is the highest r squared. We can also confirm this by looking over here at the output. And in the output right here, we see this. We see that the y should be raised to this power right here, and the x should be raised. Does everyone understand? Find transformation takes your model, and it finds the transformations that increase the r squared the most. Does that make sense? It's going to tell you a list of transformations like raise y to this power, raise x to this power, and you will get this r squared. Like you'll explain more variation by transforming these variables this way. Now you have to do it. One of my students coded it so it would do it for him. He was like, Brian, why don't I just code this to do it for me? And I was like, that's a great idea. And Dr. Peters like, that makes it too easy. And I was like, oh, well, that was a bummer. So let's go here to transformed y, and let's go here to transformed x. It's one way of doing it right here. This is perfectly fine. I'm going to go to survey, and let's go to survey 10, $, and this is our y variable. And we're going to take y, I'm going to raise it to the third power. Let's go to survey 10, and let's do weight, which is our x variable. And we're going to be careful because we need to put this in a parentheses and do that. Always, sometimes just, maybe, I don't know, we could put this in a parentheses. Why not? Now, when I run my model, I can take and go to m save into, no, I should call it maybe m transformed. And we're going to go here to lm because I'm just saving into it. I'm going to take my transformed y, tilde my transformed x. Now, what people might be wondering is why don't I have data equals? The reason I don't have data equals is because these are just vectors outside a data frame. Do you see how these do not exist? Does that make sense to everybody? That I'm not doing y tilde x comma data equals. I could, if I want, store them inside the data frame. Just so you can see I can store them inside the data frame. I'm just going to open this up. Let's go down here. And now if I do this right here, they will be stored inside the data frame. So I am now storing the vectors inside the data frame. Does everyone see the difference in the code that I just did, where the first time I ran it, I stored them in the values in the global environment. And the second time I ran it, I stored them inside the data frame by doing survey 10 $trans.y, and it's stored right there. Now, either of these codes will work. This will work because they're stored inside the global environment right here, or I can do data equals, and data equals will work because I have them inside of survey 10. So that works too. You don't need to do both ways. I'm just showing the theory behind we could put them in the data frame or we could put them in the global environment. It's a point of preference. So let's go here to check regression, see if it fixed it. And we're going to do our transform model, and let's take a look. And hey, we got a condition that passed. What condition is good? What condition is good? What condition is good? Should be able to see over here. 100 points first person. What condition is good? Following along. You should see instantaneously. It's barely good. It's barely good. It's, who knows? Should be like, up. No, which condition is good? Got it. Yep, Sylvia. Amazing job today, Sylvia. Equal spread and Brad right there. Equal spread is good. Other conditions are not so good. So we don't need to worry about equal spread when we look at these. We need to look at the linearity. Linearity is not so bad. The model's not horrible. I mean, it's kind of this is a huge iffy one. And remember, sample size is just whether we continue or not. So we wouldn't say sample size is good. No, good question, Emily. 100 points, Emily, right there. So we don't say that sample size is good. We just say if sample size allows us to continue. So don't worry, this is something that, so sample size is not really a condition. It's just if we have a large enough sample size, we get to continue. So if the p-values are low and the sample size is small, then we're done. So it's not that we failed the sample size. Don't worry, that I paused here because I've seen a lot of people say we failed the sample size. It's that we don't get to continue. We don't need a big sample, but if the sample size is small, then we need to do well on the conditions. So there's 3 conditions: linearity, equal spread, normality of residuals. And if we have a small sample size, we need to get p-values above 0.05. Because if we have a low sample size, then we fail if our p-values are bad. So don't worry, that is like something I always like to stress, is that the sample size is just a check to continue. It's like, okay, we can continue on because we have a large sample size. So there's our transformations. Let's hop back into the notes right here. Go back over the main screen here. I need a 320. Maybe, I don't know. I need to work on this weekend. And so here's where we're just doing the transformation. If you notice, we have our X and we have our Y, and we're plotting it, we're transforming it. Things I was doing just a moment ago. When the fine transformation looks, it also does the log-log transformation, just the way it does it mathematically. So why we log stuff is for extreme values. Extreme values, which do we have a log version on here? Not on these slides right here, but extreme values will be best pulled in by a log. If you work in finance or accounting, you'll have usually currency numbers, and currency can be very, very large. And because of that, you might have someone who has like 100,000, a million, 10 million, 150 million, and it'll pull in the extreme values if you do like a log 10, where a million with a log 10, I believe, is 6. Someone correct me if I'm wrong. I believe it's 6. And then a billion would just be 9. So if you look, a million and a billion are just separated by 6 to 9, and 1,000 to a million is 3 to 6, because it's log 10. It's what power do you raise 10 to get a million? You raise 10 to the 6. So logs pull in extreme values. They bring data that's skewed and normalize it. And that's our goal a lot of times, is to create normality in data. We talk about that a lot in 474. So here's our model right here, or here's the code. You saw me do this code a moment ago, where you make your model. Here's step 1, defining transformations. So write these down. Step 1, defining transformations is 1, make your model. 2, find transformations. So you can see here, step 1, make your model. 2, run find transformations. 3, after you run find transformations, create your model using the suggested powers. Great job, chat, 100 points. Keep writing those down. 1 is make your model. 2 is run find transformations. And then 3, create the model from that's suggested in the output. So now that's probably the hard part, because you notice here it says raise your Y, which is shell weight, to the associated power. So we have to take shell weight, and we have to bring shell weight to this power here, and then we have to bring length to this power here. Now, once again, the notes show you how to do this right here, right here. So this is step 3. Step 3 is right here, showing you that, as we said, shell weight is going to be raised to the negative 0.75 power. And why is it raised to that power? That was the power suggested right here for the Y. Just to make it very clear, this is the power we're raising shell weight to, because here's shell weight, that's our Y variable for these abalone fish thingies. And then we're going to do it right here. So connect these dots right here. The reason this is happening is because shell weight was suggested to be raised to this power. Now, one of the things with transformations is you lose the context the data's in. But look at your R squared. You went from explaining 76% of the variation all the way up to 95. Imagine this. Your friend says they'll drive you to New York, and they'll drive you 76% of the way there. Another friend comes along and says, well, I'll drive you 95% of the way there. Does that sound a good bit better to you? 76 to 95. That's a lot. That's a big difference. That's like getting up to like maybe Maryland from Tennessee, maybe. And this would be like up to Maryland, and this would be like you're right outside the state. Like you're pretty much there. Like, okay, I'm good. I guess got another 5%. I've got another, I don't know, 40 miles. Pretty good. You're like, oh, I'll run it. I wouldn't run it. Be a long run. Catch all the Pokemon. Almost out of Red Bull. It's got to kick in this morning, Brad. And so right here, you can see the differences. Here's our original model, which you can see immediately in this plot that the linearity is an issue, the equal spread's an issue. And look at this new plot. If you were to look at the conditions, so it's 66. Oh, it's kind of close, Sylvia, right there. Kind of close. I've got some family in Maryland, in Bowie, Maryland. So if you go right here, you can see there's a bit of a problem with equal spread out here at the end. So the problem's going to be like equal spread. Oh, cool. Maryland's pretty nice. I went to a few different places. We got multiple people from Maryland? Maryland, wow. Shouts to Maryland. Popular place. And here we go right here. Here's how we transform the x. Pretty easy right there to see. And you can take log 10. This is how you take log 10. Please note these slides. This is on this next assignment due tomorrow night now. Thank you for everyone who suggested that. I'm always open to suggestions. Remember, you guys ask. The only way to know is to ask. And sometimes we'll do it. Sometimes we won't. Never know. And then you can check your conditions. How do we do after the transformation? How do we do after the transformation on all the conditions, good or bad? We transformed it. Yay, we transformed it. How do we do on all the conditions? How do we do it on all the conditions after transforming it? How did we do? You would think. We did bad. Yeah. We did bad. So we still did bad. And as it says, and the sample size here is good enough for us to continue. Remember, we don't really pass the sample size, but because we failed all the conditions or any of the conditions, if you fail any condition, you have to look to see if you can continue. So here's step 1 on the flow chart. We failed all the conditions. That's bad. We look at the sample size. We can continue on because the sample size is greater than 25. So, or equal to. I don't care. I'm never going to be like, is this exactly? No, it doesn't matter if it's exactly. Oof. I mean, there's no curvature, as it says, because the line goes through the middle of the data. That line goes through the middle. I do like to do questions like this on the test because I'll put this up and I'll be like, is the linearity condition good? This one's hard to look at, but a lot of times people will look at this. I like it when this one looks bad because people will think that this is the linearity because they'll see this line. But this is the line for linearity. That's the line for linearity right here. This is the red normality curve. So the normality is ridiculous. I could say this is a good way to just catch people who don't know. I could say, like this problem, this test looks to have a major problem with normality or linearity. Would you guys love this if I put this graphic on the test? Alex, if you're watching, please put that in the practice questions. Like this graphic seems to show a problem with the linearity or the normality. Would that be a pretty obvious one? Which one's the problem here? I mean, like, I can't tell if linearity is perfect. Linearity does have a problem according to the p-values. Yep, this is and that's the normality. And there's huge problems here. These problems right here are massive. So that just jumped, for anyone who does stats, the QQ plot here is extremely not normal. Does that seem like a fair question to everyone, especially if you know it in class? I like it because I'm not trying to trick people, but the people who don't know how this works would be like, well, it looks like the line doesn't do a good job, but that's a normal curve right here. It's that red normal curve. So I do like those types of questions that kind of, it seems like it's like spread is pretty, Brennan right there, 100 points. Yep, spread is the other big problem. Tiny little spread here, moderate spread, a mega spread. And that's only a few points too, which is really bad because when you have less points, usually you have less spread. Like that's the way it works. When there's less points, there should be less spread because there's less data to be randomly distributed. And so there's very few points and there's large spreads. So that's a big problem. Huge problem. Brennan, 1,000 points. Like that you mentioned that because that is the other big problem on this. Linearity's okay. It's no big problem with linearity. Linearity's fine. Like I can't see a problem. I don't visually see a problem. So when it comes to untransforming, What is the goal of untransforming variables? When it comes to untransforming variables, you need to know this for your assignment. The goal for untransforming is to simply untransform the y. Do not worry. I would literally just take it, and I need to tell the grader this grader, if you're watching, I need to send them an email. I would literally just take it, and if somebody raised this to the what power, I'd be fine. I'd be fine if someone just raised this side right over here to the what power, which is almost that, because this is -3/4. So you could just raise this side over here to the what. If you wanted to just fix this really, really quick, you could raise that side over there to the what on the right side. And then I just leave it as that. Be like, cool. I'm not here to do algebra. Well, think about this. How would you undo if something is, yes, Mila, that's right. Mila's right. -4/3. Because right now the left-hand side is raised to the -3/4. So since this side over here is raised to the -3/4, does that make sense to everybody? Let me go to the screen. This side is raised to the -3/4. So how do you undo something that is raised to the -3/4? You raise it to the -4/3. It's the reciprocal. And a negative times a negative is a positive. The whole goal over here is to make this just this. That's the whole goal. The whole goal is to untransform the y. We just want y equals and then an equation. I don't care how this side looks because I'm going to let the computer do all the work. You don't need to algebra it down. I mean, it's nice to see, but the whole goal is that shell weight no longer has a transformation. That way, if somebody, think about this. Somebody tells you their x, they could tell you the length. The length is going to go through some sort of mathematical calculation, and then after that, it's going to tell you the shell weight. Originally, someone told you their length, and when they originally told you their length, you would get their shell weight in -0.75, raised to a power. So you'd get this weird thing. Would that not change the models? Nope. It'll just change, it changes the math, and we'll let it still do the work, but it would give us it in the untransformed value of the y. It'd give us the untransformed value of the y. So it does change. It's just reordering the mathematics in it. So all the math would still be the same, and you're just writing the untransformed equation. Do we have another example on the slides of untransformed equations? We show how to do all the untransforming. So when you're doing your homework assignment, if you're wondering how to untransform stuff like logs, so I'm not going to spend too much time on this because it's all here, like how to untransform. It's just an algebra primer, and it shows you every little thing. Oh, we have outliers, and then we'll be done with this chapter. But it shows you how to untransform like things to powers, negative powers, half powers, all these things right here. Shows you how to untransform logs. So when you're doing your last few questions, I think there's 5 at the end of the assignment, do this right here. Also, here's my suggestion. My big suggestion when doing them is knit your document. This is Brian's big suggestion for the homework, is knit your document and then go to insert and do the equation builder. Let's go to insert equation builder, and you can do things like y equals, and this is going to be 50 times easier. If someone knows, you can do LaTeX, you can do all that, but this right here is going to be 100 times faster for most people. You can do, if you know how to do LaTeX, LaTeX, which I know a little bit how to do it, but that's what the code is you're seeing, but just knit your document and then untransform the y. Like if this had been originally, let's take that and copy it. No, survey $10 sign. Here we go. Let's do this. Would this work? This might work. How? Sure, why not? Why not? How would you untransform this one? Oh, I'll do a log here too, because those are the tricky ones. How would you untransform this? How would you there we go. How would you untransform this? What would you do to both sides of this to untransform this? What would you do to both sides to untransform this? So I think I'm inside of R when I do that. Square root both sides. Yep. So you could take, and that's just going to be y. And I think I can highlight and do that. Oh, no, we don't want to do that. Well, sure, why not? That works. And maybe you want to put this inside of a parentheses, or you could do this. Please tell me if you think the grader graded it incorrectly, but that's square rooting it. Or you could, I guess it'd be weird, or you could put a cubed root over, or a fourth root. I think that'd work. As long as you think it's mathematically accurate. But if you, because you can times this power by the half, and that does that. So you can times that power by half, that power by half, and then that's square root of square root. So that's perfectly acceptable. Like that's perfectly fine. The confusing ones, well, let me do a log one, because even I'm going to be like, wait a minute. Logs are fun. Everyone agrees. Who thinks logs are fun? So when you deal with logs are the most fun. Let's do this. All right, here, let's put in a log equation. Insert. Let's do where it was log y and log of y. And let's do log 10. Log 10 of y equals 2x plus 5. Okay, right here. Not a chance. Bane of your existence. So the way to undo a log is you have to take everything. And truthfully, I'm fine with this. I need to tell the grader as long as it works. You know what? Easiest way to undo this is you take your equation. And how do you undo a log? A log needs to connect with its what via the what. I can see it in my head visually right here. To undo a log, to remove the log in front of something, you literally have to take, and I'll show you the steps of it. You have to take this. It's going to be easier if I do this. Yeah, Emily, 100 points right there, Emily. Great job, Emily. That is correct. So you need to go here, and this needs to go in the exponent. So you raise everything to the power of the log. So this is log, and it has to be raised to the 10. So we're showing the steps right here, and then this right here is also going to be 10 raised to the power of this. And since those are it's fine, you can leave it like that. This cancels now, since the whole point of doing this right here was just to cancel this out. So here's the steps right here. So that canceled. That's reduced. And then since you're adding that, you can separate that. So you can, please tell me if I'm wrong on this. This is where my brain's like, can you? Because this is fine. This is solved. And I would maybe, just so people know, put this in parentheses, just so it looks a little. But now you can separate this, because if you add things in the exponent, please tell me if I'm wrong, math people. Nitin in our next class is a math PhD. Nitin, please tell me if I'm wrong. There goes that. And so this could also be reduced here. Sorry, I'm going to answer questions here in a moment. Hopefully people are, you multiply? Oh, it's multiply. It's multiplied, right? I knew there was something wrong with that. So it's multiplied, right? Not add. Oh, Mila right there. 1,000 points correcting me. Thank you very much. I knew something was wrong. I was like, something is wrong. That's why I don't do math. There we go right there. So there's that. And that's got it. So yeah, little error. Raise the log by its base. So does everything look right here, Mila? For my math people, every time you say log, yes, I did that like a few days ago, and no one, Brad, 100 points. You're the only one who knows. Like, it's log. It's big, it's heavy, it's wood. And everyone's like, what's going on? I don't know what that is. Brad, gotcha right there. Nah, I don't care. This is fine. That was good. This is an answer. It's the way it works. Simplifying just creates problems. So if you notice, even I'll make mistakes because I don't algebra all the time. The biggest thing is undoing the log. Once you get it to this, it's fine. From here, it's the same mathematical. The whole point, what is literally, as the slides say, the whole point is to get what? The whole point is to get this. So, yeah, math is hard. I know, right? The whole point is to get this y. You could put it into Wolfram Alpha, probably. I don't care. I mean, seriously, just if you want to put it into Wolfram Alpha and say solve for y, or I don't know if it'll reduce it, like if it'll untransform it. But, yeah, I'm fine. As long as this is y. That's all that matters. I don't care how the other side looks, as long as, and that's the thing. Please look at how this is graded. We've done questions like this every semester, and sometimes the grader's really accurate. Sometimes they think they have to grade exactly by the key, and I tell them, You know, if it's right, it's right, as long as they get the right answer. So please look at your grades. Few people have emailed me and gotten points back by looking at their grades. Try not to wait till the very end of the semester. Be like, Brian, on assignment 1, this, assignment 2, this. I'll be like, okay. You know, I mean, I'll try to look at it all, but try not to email me at the end. That makes it very confusing and very, I don't know, hard to like make adjustments and look through everything. So be looking at your grades as you get them. I do, you know, want to hear from you, especially if you think something wasn't graded accurately. Has anyone here emailed me and gotten points back? There was a thread in my hair, a plastic thread. What the heck? What's from this? Yes, exactly. So please email me and say like, hey, Brian, I don't think this was graded properly. Yeah, just look over your grades. Look over what the grader marked. Be like, I don't know why I lost points. You know, like, it's fine. Just tell me what you think. It's the way it goes. It's a conversation. Awesome. Yep. So there's help right there. Last thing here with outliers. Then we're going to start up some multiple regression to start things out. With outliers, what can outliers do? I think outliers is very short here. What can outliers do to a regression or a correlation? What can outliers do to a regression or correlation? 100 points first person. Anything, Brad? Yep. Anything is possible with outliers. So we'll look more in multiple regression, how they can impact it. But I can't make it more clear that outliers can make it weaker, stronger, positive, negative, you name it. Outliers are going to do anything to it. So this is why we say Q, straight enough. No outliers. We don't want the outliers. Plot doesn't thicken. So the outlier is generally typo and error. So you can remove outliers if they're just wrong. Like if someone entered a typo, that's it. We'll go more into that in multiple regression. But, you know, things like that could be on the test because outliers impact correlation. So we did talk about how outliers impact correlation. But now it is time, and I'm so glad we're getting to where I want to get today. We got this. It is time for us to go to multiple regression. So we did transformations today and kind of a talk on outliers, and we reviewed how to check conditions. So how's everyone feeling? Has there been a lot of material today, or like it's feeling pretty good? I'm gonna hit you guys with more material. Do you feel like we kind of reviewed yesterday's material? We made sure we understand how to do all the tests. I feel like we have that really down, lots of practice. And we talked about transforming models and untransforming. So we did how to transform, how to untransform, all that good stuff. And one of these days I'll get headphones that just don't fall out of my ears. Good. I feel like it's a pretty smooth day, and I want to say this feels good. Awesome. Thank you so much, Sylvia and Nicole. Feeling pretty good. Not too much, but definitely need to brush up on my math skills. Yeah, don't worry. The tests won't be too mathy. Once again, if I'm asking you to untransform something, I'll ask you to untransform like a squared y, or not, you'll unsquare. Those are some of the easiest problems on the test. And I was, you know, and you can't write them out now, but the math in this class, don't worry. Don't worry about being like, oh, this weekend I got to study up on math. No, don't worry about it. You can always reference things, and Wolfram Alpha. We utilize math to help us out, but we don't need to be math experts unless you want to get a PhD. And I did, and I needed better math skills. Real analysis, oh fun. But if you can't tell, I loved it. So differential equations. Differential equations is the bane of my existence. I cannot just get some diffie-q down. Get ready for multiple. Now, here's the thing. When it comes to multiple regression, this is why I'm glad we're getting to this at the end of this week, and we'll have our first assignment. What you're going to notice is multiple regression is just like simple regression. Everything we've done in simple regression is going to carry over into multiple regression. Just to show you. Let's find a part right here. Wait a minute. Check regression? We were just doing check regression. How many things are there that we check in check regression? Any ideas? It's on the screen. How many things do we check in check regression? This is why such a strong foundation in simple makes multiple like that. 3, Brad, 100 points right there. It's 3. What do? We look at the p-values. And great job, Sylvia mentioned earlier there were not enough duplicates, which means, we just can't do that test. So we're like, well, I guess I don't know the answer, whether or not. Who can figure out for 1,000 points, how many tests are failed right here? How many tests are failed? First person, how many tests are failed? 1,000 points. I totally mean it. So I'm making big points for the end of the semester here. Be showing up, know how to answer these questions. How many tests are failed right here? Okay, I think I know the answer. Boom, Meal right there with 1. And Brennan and Meal are getting the points too. It's 1. It's only that one. Unless I'm looking at it incorrectly. 100 points everyone else. Getting your 200 points today. If you get the 1,000 though, you break the rules and you got crazy amounts of points. So Meal and Brennan got the 1,000 right there. And you can get up to 2,000 points from Brian's crazy points. And then you're capped at 2,000. So I think Sylvia's there too, because Sylvia's asked some amazing questions. Thank you, Sylvia, very much. If you think of big questions, be asking them. Be like, Brian, I don't understand what's going on right here. Do we have another one? Oh, so here's the normality plots when we look at them. And here's the linearity issues. Here's the QQ plots for normality, which look good, and we don't see bad ones. How many conditions do we pass or fail here? Who can explain really quickly how many conditions we pass or fail here for this one in a multiple regression? We haven't even done multiple regression yet, but we can look at the conditions. How many conditions do we pass or fail here? Should be able to see it like that if you know how the conditions work, which we were just covering a lot today. Boom, Sylvia, yes. Yeah, Brad, right there. We all are failed. We fail all 3. We fail linearity for everything, including all of our x's in the model. And then we fail for equal spread, and we fail for normality. Everything is failed for every x and for the overall linearity of the model. And I'll go into more detail when we get to this, how we have, I think it should be pretty easy to see, we have a linearity now for each of our x. So every x gets its own linearity. And then the overall model has its overall model linearity. So you do the linearity for each of the x, and you do the linearity for the overall model. So that's what's going on right there. But does this seem like, do you get what's going on here for checking conditions for multiple regression? Does that make sense? P-value less than 0.05, so reject the null is bad. Correct, Philip, 100 points right there. Why not, Philip, 1,000? I love that you added that in. Yep, and then here's the plots you get. Okay, let's go back in time. We just literally covered like 8 or 9 slides like that, and hopefully we're like, yeah, that makes sense. We just did that in simple regression, and that's the way this should kind of feel as we go through and start talking about the super scary multiple regression. What does the word multiple mean? 1,000 points first person to explain to us what multiple means. What does it mean that we have a multiple regression? You just kind of saw it. What's the difference from simple to multiple? More than 1x. Boom, right there. Brennan, I think Brad, Brennan, Sylvia, you're at the 2,000 today. Crazy points. That's the answers I want to hear. So we've got here, this right here, we have more than 1x is in the model. More than 1x. Great answers right here. We're following along. We know what's going on. When we say a multiple regression has included within multiple x's. That's all it means. Simple regression, 1x. Multiple regression, multiple x's. Pretty easy to understand what's going on. So when we write our equation for simple linear regression, very easy to see here. It's just the predicted value of y for an individual is equal to some true intercept plus some true slope times the x variable we have chosen. And then we have here an error term. These, like, it's just a miss, a random disturbance. And the random disturbance, which is pretty much a residual, the random disturbance is the true disturbance. Like, if you're wondering why it's not residual, it's because this is for the true model. And it's weird to say this, but the true model wouldn't be wrong. Something would miss the true model. So because it's the truth, it's the equation that explains reality. And once again, these are like holy quantities. It's like this nebulous thing that if we had all the data, we would know, but we don't really do that in statistics. This is like the theoretical true model that exists. And so we use estimates down here of these theoretical quantities. So we don't really even use this, but we have assumptions about what we're trying to understand, that the disturbances for the true model should be normally distributed. There's your linearity, there's your normality of residuals. They should have a mean of 0. There's your linearity condition, and they should have a constant equal spread, which is the last thing right here. The spread should be constant at all times, homoscedastic. So there it is right there, the key assumptions we have. So once again, this is review. We often use right here our model to predict either the individual, and this is what we talked about yesterday too. This was a what interval? Hint, 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 first person 1,000 points. When we do the individual, what kind of interval are we making? Right there, that's a huge hint. 1,000 points first person. When we do intervals for individuals, we're doing a what interval? On your assignment for tomorrow, and 1,000 points first person. What kind of interval are we doing? Boom, Mila right there. And Philip, wait, no, wait. Someone else needs to say it. Mila, you're at 2,000. Great job. Keep answering, Mila. Casey also got it. We're doing a prediction. And was it Nicholas? Sorry, Nicholas. My eyes blink. Nicholas, you definitely got it too. So prediction interval. First 3 people right there. So keep paying attention. And then what's the other type of interval we can make? First 2 people. I'm trying to give away some big 1,000 points today. First 2 people. What's the other type of interval we can make for using our model? We can make a prediction interval for the individuals or confidence. Brennan and Mila, great job. And Philip, I think that puts Philip at a 2 right there. So great job. Okay, let's do this. Limitations, once again. So here's the limitations, why we go from simple linear regression to multiple regression. Going from simple to multiple, you have to realize that we're just including more x's. So we have, I think it's the Kroger data. No, we don't see it yet. So this is just the model here. Pretty easy to notice. All you do is this is the coefficient of the first x. This is the coefficient of the second x. This is the first x, if I could highlight it. This is the first x. This is the second x. So we have right here all of our coefficients for each x. There's a coefficient and then an x. Coefficient, then an x. Coefficient, then an x. Coefficient, then an x. All the way up to how many ever we have. The reason it extends out this far, it's like saying you have k x's in the model. Like we're just going to go through and say for each x, it gets a coefficient. It's the weight of the variable in the model. So this is why we don't use y equals mx plus b in statistics, is because it's easy to see that the intercept is when all the x's are equal to 0, and it doesn't have an x. The intercept has no x. It's sometimes called an offset in other models, like neural nets. I'll tell you about neural nets in 474. So the intercept has no x. It's when all the x's are equal to 0, and then each x, respectively, like the first x, has the first coefficient. So it just makes sense when you think about it to say like, well, we have here the intercept, and then we have here the coefficient of the first x times the first x, plus the coefficient of the second x times the second x. And then what do we still assume about all of the disturbances? They're still, once again, have the conditions of normality, linearity, and equal spread. Big conditions right there. So you can see all 3 conditions. Kind of understand the residuals will be, the disturbances will be normally distributed with a mean of 0 and a standard deviation that is constant. And that's why it just says sigma right there, because it's one constant standard deviation. And yeah, that's just a review of everything I'm saying. And here's the model we're actually using. So once again, if you notice the small switch right here, all of these betas become Bs. That's it. And then we're predicting either for an individual or we are predicting for the whole population. So we were mentioning this previously, that when we do this right here, we're doing confidence intervals, and we do this right here, we're doing individuals. Like we can't. Here, let me show you the key part of this. This is for everything. This is for individuals. So Kroger wants to first person, prediction or confidence. Kroger wants to figure out how much a certain customer will spend yearly. They want to make a prediction or a confidence interval. First person get right, 1,000 points. They want to make a prediction or a confidence interval. They want to figure out how much a certain person who lives in such and such, boom, right there, Casey. I think because Mila, Casey, I think Grant's the first person I haven't given the 1,000 to. Casey, Mila, Sylvia, you're all at 2,000, and Grant gets 1,000 right there. Send me those points, Grant. Big points right there for you, Grant. Great job, Grant. And Mila, Casey, and Sylvia, great job. I don't think I've given the points to Grant today yet. Great job. So it was definitely prediction because it was an individual. So remember, predictions, if you remember right there, are for people. So that's a good way to remember it. Predictions are for people. Does that make sense? When you do a prediction interval, it's for people, kind of like the alliteration of predictions and people. And confidence intervals are for the whole population. So this is when you're doing a confidence interval right here for the mean of y given some x. And so very important we know this, the difference right there between prediction intervals and confidence intervals that the regression model makes. And here's our first multiple regression. This is all it is. Hopefully you feel the same way as I do. Philip, amazing notes in the chat. Philip, you're at your 2,000. You've put so many great notes in the chat today. Keep doing that. So when people are watching the video, they're reading Philip's notes, and they know this is what I need to know, that prediction intervals are for people and confidence intervals are for the entire population. So when Kroger's making a prediction, if they were to get a confidence interval from this, it would be all people who live 10 miles away who have a family size. Oh, we haven't done it yet. I was like, they don't have a family. That's the coefficient. For this one right here, you notice this is distance. This is all people who live 5 miles away, if this is a confidence interval they're making, who have a family size of 4 and who have an income of $50,000, if they're going to make a confidence interval from this. Now, this is just the prediction. This is just their prediction, which would be the same for an individual or for the population. But why does the intercept not make sense right here? Why does the intercept of 350 sound illogical? The intercept of 350 would be somebody who lives inside of Kroger because their distance is 0, or right next door to it. You'd be like, well, maybe right next door, and they have a distance. Okay, they live right next door to Kroger, and they have a family size of 0. Well, okay, you're like, okay, well, they have no family. Okay, well, okay. And they make absolutely no money. And maybe, depending on how you define what the variables are, like, okay, they live right next to Kroger, they have a family of 0, which would, unless you define, like, how many family members do you have, but if it's how many people are in your family and you have to include yourself, like, I'm from a family of 5. I have a brother, a sister, a mom, a dad. So I've got a family of 5. So I wouldn't say I have a family of 4 because I would count myself. So the most illogical thing, because it's possible for someone to make no money, it's possible for somebody to live virtually next to Kroger, but the only illogical one that I think cannot exist is you can't have a family size of 0, because usually we do family sizes like you count yourself in it. So this intercept itself does not make logical sense. Does that make sense why the intercept now is... A lot of times in multiple regression, the intercept is usually just illogical because everything has to be equal to 0. It would be, we would expect on average for people that live right next to Kroger, have no family, and make no money for them to spend $350 a year. Now, that's not what this model is predicting right now. It's for people who live 5 miles from Kroger, who have 4 people in their family and make $50,000. We expect them to spend monthly on Kroger $350. So this is the expected amount that either a person or people on average, because it'll predict the same thing whether for people or for the all people, a singular person or multiple. And that's not the interval, because the interval for a person will always be wider than the interval for all people, and it'll expand around the prediction. The prediction at the center of these intervals will be the same. Who thinks they understand that the prediction that both intervals are centered around will be the same? That can be best shown visually right over here. We just showed one of those plots. Can we? There we go. So the interval, if you look at these intervals, so here's your confidence interval, which this interval is doing horrible. The confidence interval has the red line at the center, which is the fit, and then this is the prediction interval right here, and it literally says prediction interval. So both of them have the same center. They have the same prediction from the model, and that prediction you're seeing right there is the prediction you're getting right here. This prediction right here that the model makes is this red line. So that is the prediction it's making, but the interval for the population, which is the confidence interval right here, is going to be tighter than the interval for an individual, which is wider. So this is the individual interval that I'm going across, and this is the interval for the population, which is tighter. Key things to note, and we are reviewing simple linear regression by reviewing multiple. Okay. And so we still have our uncertainty. Once again, standard error just means uncertainty. That's a note you should have, that standard error is just your uncertainty. We can have an uncertainty when predicting the mean of y given some x, which you just saw that visually right there with the interval that was very tight around it. There was less uncertainty. Or you can have your uncertainty when predicting for people, which there was more uncertainty. This is the uncertainty we have when predicting an individual's value, which is going to be our prediction interval. Remember the P right there, prediction interval. And then here, we'll be careful because that does say population, but this is for all people. And this is the mean of y given some x right here, and it's for all people because the mean is the mean for the population. Key things to note. Standard errors, once again, are just uncertainty, and we do want small amounts of uncertainty. Now, how do we make these intervals? This is review again. A 95% confidence interval. Philip, amazing notes. A 95% confidence interval is just usually 2 uncertainties. Now, you don't have to worry about doing these by hand. I know I'm jumping screens, but let's see it. Because, watch this. If I were to make a crazy model right here, which I've made some crazy models today, I'm going to go up here and I'm going to put in all of my x's with this. So now, that's the graphical error again. Now it goes away. Watch this, confident, which gives us confidence intervals. And look, There you go. There's 95% confidence intervals for all of the coefficients in my model. There's 95% confidence intervals. And one big thing we want to note is that these confidence intervals will be statistically significant if they do not contain what value. Here's a huge note. What value in a confidence interval would tell us that it's not significant? What value do we look for in confidence intervals for coefficients? What value? We still got 5 minutes. That's for p-values. And Nicholas is right. Brendan and Nicholas, 1,000 points each, taking some guesses right there. And Nicholas, you are right. In a confidence interval right here, and this is a big note because this is where people get confused, we look for 0. This interval does not contain 0. And think about this. You're telling me the coefficient of desired weight is not equal to 0. Like, it's probably between negative this and positive this. And if I look at my summary, desired weight, let's go to desired weight, has a coefficient that is statistically significant. Does everyone see that this is statistically significant? Now let's look at GPA. GPA is not significant. So since GPA is not significant, should 0 be in our interval that we think could be the truth for the coefficient of GPA? So once again, I think something might help here. Let me do this. Options, SciPen equals 10. And let's look at the confidence intervals. Cool. So here's my confidence intervals. You can see that, let's look at GPA. And what's in the interval for GPA? What is in the interval for GPA? And that's how you change scientific notation in R. What is in the interval for GPA? What is contained in that interval for GPA? Be very careful. Ooh, it's a good test question. Brennan, you're right. If you said 0.05, it is true, or at least negative 0.05 is in there. But when you look at this interval, we're seeing, does it contain 0? Because you'd be saying to me, the coefficient of GPA might be 0. And if something has a coefficient of 0, what impact would it have on our model? If something has a coefficient of 0, what impact would that variable have on our model? If it has a coefficient of 0, it would have an impact of what? Any ideas? To say this, oh, this might have a coefficient of 0. That's like the weight of it in the model. That, not that it fails. No, these aren't p-values. It would have no impact. Exactly. So think about that. I know there's a lot of small numbers being thrown around. But to say that GPA might have a coefficient of 0 is to say that GPA should have no impact. Because remember, we're going to take these coefficients and we're going to write out our model with it. So imagine you were to go here and you were to put in front of distance a coefficient of 0. Yep, and that's what you want to see. It's like you're saying that coefficient right there, it might be 0. So if it might be 0, you're saying distance would not impact the amount someone spends. And these intervals right here that we're looking at are trying to estimate what the true coefficient is. And we're saying, well, maybe it's negative, maybe it's positive. So wait a minute, maybe GPA is associated with higher heights, or maybe GPA is associated with lower heights, or maybe in the middle here, GPA has like no impact on it if it's 0. So I don't know if GPA should be in this model because GPA, as we saw, is not statistically significant. We don't know if it really adds new information. We're on that tomorrow. So when you look at the coefficient of GPA, it's very small and it has a lot of uncertainty. Does everyone see this is the coefficient, very small, and the uncertainty kind of outweighs it, and thus it is not statistically significant. So hopefully all this right here can be seen. Let's see. I might just do a little tiny bit of, we got only a few. And we talked about conditions. I'm seeing where I want to start tomorrow at. I'm just trying to put in my head. So we'll start with definitions. So we understand. Let's ask a few questions. I'm not going to do any more new material. We'll end class now, but don't leave yet. I'm going to ask you guys, gals, a few questions here. Let me click back to the main screen. Oh, it's taking a second there. It's being weird. So with this right here, how do people feel about multiple regression so far? How do people feel about multiple regression? Do you feel like not going to be so bad? It's just adding more variables. We're just going to do the same thing. Hopefully you kind of feel that way. Or you're like, oh no, this is that. If you have a good understanding of simple, which we've been covering pretty much all week, so far so good. I like that right there. So you feel okay? Awesome. And I think some people, I figured out one person who has like 2 accounts. If you have 2 accounts, please tell me. I've been trying to keep people's accounts straight. Sometimes people log in on like, hopefully I've got accounts like, so you might know who you are. Like, I think I finally figured out that your points have been split across 2 accounts. So I'm trying to fix everything. So if you feel like your points aren't, please talk to me. Little overwhelmed, but doable. Just need more studying. Yeah. Can you go over 3A on the homework? Yeah, let's do it really quick here. Let's go to 3A on the homework. What is 3A on the homework? Everyone's like, thank you. Is this it? Am I on the right one? I think I am. Is it homework 6? Homework 6. This looks to be about right. Oh, you guys can't see. Ah! I don't know why it's taking so long. I need to reset the computer. 3A. Load in EX3 body fat. EX3. Brad, are you still here, Brad? I'm gonna drop some old school memes in the chat. There used to be these G.I. Joe memes. If Brad might remember this, or someone else might remember it. Do you remember the G.I. Joe stuff from you remember G.I. Joe, obviously. But from the early, 2005 or 2004, there was the fake G.I. Joe PSA announcements. And my friends and I used to always, quote that, there's all the famous quotes. I miss it. And last summer for 320, I got them quoting it too. And they would say the quotes to me. They started watching the old school G.I. Joe PSAs. I don't know. They're random. Some of them I find funny. Some of them I don't. It's just, I don't know. It's someone's like, I like Rick and Morty, and someone else is like, I don't. It's all personal humor. Some of them I think are really not that funny, but then some of them just crack me up to this day. You don't remember that? I don't know. There's some really funny ones. It's funny because some of the ones people love, I'm like, that one's not that funny. I don't know. It's just, maybe it's those things you watch with your friends, you start cracking up. But see, someone's gonna pull one up, and because the G.I. Joe things were so ridiculous, and then they just re-edited them to make them even more ridiculous. So, fit model predicting fat from triceps. G.I. Joe. Just hearing it. But it was just, I just remembered vividly last summer that they started my students just, yeah, it's, my favorite one is the, hey kid, I'm a computer. It's just, it makes no sense. It's just, I didn't even watch G.I. Joe growing up. Wait, make a ball predicting fat from triceps, good. I didn't watch G.I. Joe growing up. So I don't know. People were like, "Oh, that's so and so from G.I. Joe." I'm like, I don't know who that is. I didn't watch G.I. Joe. I watched Transformers, He-Man, Garfield and Friends. So now I'm dating myself. Define data frame called to predict containing new tricep measurements. Okay. Let's go here. Let's go data.frame. And this is in the notes if you're wondering how to do this. You have to make sure to spell triceps correctly. And you have to concatenate a vector. I think it's 18 and 31. And then make the intervals right here. And the thing, too, this is also in the notes. I've got some stuff from yesterday's notes. Brad, you're going to watch the least funny one, hopefully. We'll see what Brad thinks of it. He's probably just going to watch it and be like, fine, whatever. I don't get this. So right here, you can make the predictions now. Predict using model M. That just does all the predictions. And then you go new data equals 2.predict. And that should, but now we got to do interval equals confidence or interval equals prediction. So, and this is in the notes a little bit from yesterday. I haven't posted interval equals confidence. There we go. And interval equals prediction. Does this make sense right here? Emily, is that helping out, Emily? I think Emily asked. Does that make sense? Emily, what's going on right here with the model? There's no transformation on this model. And where is the... Yeah, awesome. And then also go look at yesterday's notes because... Not BAS 320, BS 320. In yesterday's notes, right here, I go through it, but a little bit more in depth. Oh, that's... Where did I add that up? Oh, here we go right here. Here's from yesterday. So if you look at this also, and I did it kind of a little bit nicer yesterday. So hopefully that helps out. That's how we make the predictions right here. And be careful because am I predicting for an individual or am I predicting for everybody right now? Is this for the mean of everybody or for an individual? So weird the Streamlabs is double doing it. I have no idea why. Am I doing that for the mean of everybody or for the individual? Yeah, no, good job, Emily. Keep asking questions. Good luck. Yeah, take the exam. Go take it. Go take the exam if you haven't. We'll see how the grades are. I'll head off here a moment. Remember, send me your points. Send me those points. Streamlabs. You only have to report it once. I know your graphics now awesome, but man, one that cool. But that's got it. This would be for individuals because it's prediction intervals. So this would be if your friend asks you versus confidence. That means double points. It might. I have no idea. Oh man. Well, that's got it for now. I'll be back. I click the button and it takes a moment. Click the button. Bye, buddy. Hey everybody, it's Mario time. How's everyone doing this morning? We got some video game shirts going on. Hey Anisha, hey Sarah, hey Jinning, hey Jordan, hey Andrew. Everybody, Dennis still here hanging out. Hang out, have fun. Some 474. Good morning, Peyton. Let's play a little Mega Man. This is like my get going song in the morning. It's funny, sometimes when I'm getting ready like for class, I'll just play this song to listen to, just like get hype. Be like, we got this. Time to start. Good morning in right there. Good morning, Caroline. Good morning, Andrew. Good morning, Casey. Good morning, Peyton. Let's do this. So, we have some more topics to cover today, and we have some big things to understand. This is really, we build this really strong foundation, and then we layer on top of it the topics. And we are in our final 2 weeks of classes right now. We've done 3 weeks, and we're in the last 2 weeks. And I really like how we pretty much give you the essentials for coding. We give you the essential for the background in statistics. And then we give you the essentials for the tools and techniques for data mining on how we do stuff. So it's really a 3-prong approach. We're going to make sure you can code. We're going to make sure you understand the basic stats. And then we're going to make sure you understand the tools and techniques in data mining, which that's really just the last 2 weeks here. Now, one thing I want to mention is I do have the drops currently in. So your drops in your assignments, the drops you currently have, sorry, something in my, can I vanish? How do I vanish? I'm gone. I'm back. So the drops you have are currently in. So I should have said this to 320 also, but I was looking at grades. Grades are great right now. Grades are doing great. But here's the thing. Grades are about to change in this class. Dun, dun, dun. It's like grades are about to change. They'll never be the same. Because what's about to happen is you're about to have your test, you're about to have your take home, and then some people have already used their drops for assignments. So, you might have it's all right. You might have had an assignment where you didn't do as well, but all of a sudden now, if you get a lower assignment, like maybe you get a 40 or a 50 on an assignment, that won't be dropped. So that could impact your grade more. So grades, all of a sudden I see it towards as the semester goes on, start dropping because we get the tests, we get this and this. But biggest thing, be doing the take home, be working hard on it. If you have questions about what does something mean, please email me immediately. Once again, I can't explain how to do things. I can only, and once again, don't ask people how to do things. Just don't ask people. Don't be like, how do I do this? Where do I do this? Direct all questions to me for it. That way, even if it's kind of simple, like I can't get to load, direct it to me just so I'm the only one kind of communicating how to do things. And that way it doesn't open up a conversation. Like, it's not cheating to tell someone how to make the midterm, but it kind of opens up the conversation. And please, please, please just get a hold of me as soon as possible. Does everyone have their midterm created? Has everyone gotten it created? Because at this point, you need to make sure you're at least got it created. Everyone should be there. How are we doing? What % complete are people on the midterm? You can't answer these questions. Like, wait, Brian, you said don't talk about it. I'm close to being done. Good. How many hours have you put in, Andrew? How many hours would you say you've put in? Everyone's got it created. How? 98% done, Jordan. That's awesome. 15 hours. Oh, wow. 75% done. Yeah, it's not the easiest of midterms. From what I'm noticing is the 474 respondus tests are higher, and I think the 474 take homes might be lower. Just keep checking it, make sure it's right. Just double check everything. I'm not trying to give you more anxiety, sorry. But yeah, and don't worry. Just realize obviously put good work into it. This, like I said, is our big week in the class. The final will be a big week too. Next week, we're just going to cool it down a little bit more. But this week and the final. So, and I know it's a lot going on. People have more classes. We got life. We got a lot going on. But I appreciate all the hard work. And yes, hopefully it's helping you push your mind forward and learning and practicing. So we ended yesterday with the K-fold cross-validation. K-fold cross-validation is how we select our model. So when we select our model right here, let's go back to the graphic. Where's that graphic at? This is repeated K-fold right here. Here's the graphic we ended on last class. And it's important we know exactly what this graphic is showing us. That we have here the estimated generalization error. Now, what does it mean to have an estimated generalization error? This is how we think our model will do on new data. This is how we think our model will do on new data. This is how the model will work on new data. Now, for 100 points, 200 points max today, which of these should we select from? Should we select our model by how we think it'll work on new data or how it works on new data? Should we select our model by how we think it'll work on new data or how it works on new data? I think I'm making it a trick question. It's a trick question. Andrew gets 100 points for being first, but it's a trick question. Not both. Well, that would be a real trick question, right? How it thinks right there. Everyone answering gets 100 points. Why not? We want to select it by how we think it'll work. How we think it will work. Why don't we select our model based on how it works on new data? Why do we not just select our model by how it would work on new data? Why not just select the model by how it works on new data? Why not just select it? That's why. If you select your model by how it works on new data, you've just fit it to the new data. You don't put your model to new data and just select it on the new data, or you overfit. So these are key terms we've been talking about here, because what we want to do is we want to train our model. Where's the training at? We train our model on some data, and then the holdout is merely just a final evaluation or a test. So we only use the holdout, new data, to test our model. We do not select our model based on this. We select our model on the validation portion. So the validation portion moves throughout. It's within the training. The validation portion that we see here in the k-fold for process, which k just means how many folds there are. So in the k-fold cross-validation process, the validation moves throughout through different rounds and tells us how the model does on this validation portion, which is a pseudo holdout. So what's the point of the validation? It's to have a guess of how it'll work on new data. So we then pick our model based on the guess of how it'll work. So we would pick this model right here, because this model is estimated. Look at the keyword right here for this axis. This model is estimated to be the best. Now, this model right here is not the best model on new data. The model that would be the best would have the lowest RMSE on the holdout, because this is new data. But we wouldn't have picked those models down there because they were not estimated to be the best. So you say, well, why not pick these models? They do the best. Well, then you're fitting to the holdout. Who thinks they get this idea of like, you don't pick the model that does the best on the holdout. You pick the model you think will do the best and you test it on the holdout. You're like, ooh, I think this model will work. Let's test it out. You don't say, let's find the model that works and use that model. You say, this model looks like a good model. Let's give it a test to see if it works. And then you don't know how it'll do. And if it does well, you're like, yes, it does what I thought it would do. That's a good model. And it's confirmation. Who thinks that makes sense? It was a concept that I didn't get for a while. That's why I go over these things so much. Hopefully someone has like a light bulb. Yeah. And this is, exactly. You wouldn't just, to like use that example, you would look at 1,000 cars and you'd pick from that a car you think will be a good car. And it's kind of how we do it. Then we test drive it. And then the test drive tells you if you buy it or not. But you wouldn't test drive all 1,000 cars. You're going to look at all of them. So should we always choose the furthest? You always choose the one with the lowest estimated, one standard deviation rule coming up very soon. The model that works the best is going to be the one with the lowest estimated generalization error. And this is from the what portion of the data. Everything I'm highlighting now by going to the one furthest to the left and talking about the estimated generalization error, this is all coming from the what portion. The training, the validation, or the holdout. Careful. Because this is the estimate of how it'll work on new data. It's an estimate. It's not how it works on new data. It's an estimate of how it'll work on new data. It's not how it works on new data. It's an estimate. Validation. The training makes the model. So these are key notes. Write these down. The training makes the model. The validation estimates how the model will do on new data. And then the holdout is how it does on new data. Does everyone see the process? You make your model from training. You estimate how your model will do on new data with validation. And then the holdout is how it actually does on new data. What's the point of the training? To make your model. What's the point of the validation? To help us select the model we will test on the holdout, and the holdout is how it does on new data. Does that make more sense on the process? Make your model from your training. Make an estimate of how it will do from the validation. And then how does it do on new data is the holdout. So the selection of the model is done on the validation. The creation of the model is done on the what. These are really good. Like, I need these. I wish Alex was in this class because he writes down so many questions I write, and I really am going to be referencing these. So let me ask this. The creation of the model is done from what portion of the data? The creation of the model is done from the training. The selection of the model we are going to see if it works is from the validation. The testing of the model is done on the holdout. The holdout is data that we are holding out. So what we do when we get our data, which 320 has a better graphic on it, I can draw it. I can draw. The way it works right here. So small on this screen. So zoom out. Okay. When you get data, maybe you get 1,000 data points. So if you were to get 1,000 data points, and here's your data, it's just a pizza. What you're going to do is you're going to take like 20% of your data randomly, and you're going to hold this out. So this is going to be like 20% holdout. And this means it does not make your model. And this is like 80% of your data is going to be training. Now, there's different theories we talked about yesterday about how much to hold out, how much to keep in your training. But right here, you'll notice we have like 20% holdout, 80% training. So your model will be made from this. And then within the training, we will do what? Within the training data that we're going to make our model with, there'll also be the what inside of here. Within the training, there'll also be the what. I didn't make it evenly. That's good enough. Within the training, there'll also be the validation. Yep. So when we do the validation, we make our model on the highlighted ones, and then we test our model here. And so now we're holding that out. It's a pseudo holdout because we're going to go through, this is k-fold what right now. I'm going through k-fold what. Brian's going to make his model on the highlighted ones and hold out that to test it on. He's going to make his model on the highlighted ones and then hold out this to test it on. He's going to make his model on the highlighted ones and hold out this to test it on. K-fold 5, yep. And then he's going to make his model on the highlighted ones and then test it on that. And it's evenly. Sorry, I'm just not a good artist, but you would cut it into 5 even sections, like if this is a ball of clay right here. And so if you notice, do you notice how like the holdout that I'm doing is very similar to the holdout on the other side? It's very mechanically similar, and this is why we call this red portion right here a pseudo holdout, because this red portion is going to make the model in 4 out of 5 of the k-fold 5. It's only held out one time. So when we're making our model on the highlighted portion and testing it on the portion that we're holding out, it's a pseudo holdout because that portion we held out will make the model in this time, it'll make the model in this time, it'll make the model in this time right here, and it'll make the model in this time. So it makes it in all but one time, but we're doing like a pseudo holdout. It's an internal validation to check for an external validation. So who feels like this makes a good bit more sense now that when we get data, we'll have 3 portions of the data. You have your training, which is highlighted, and the k-fold cross-validation process will permeate through what portion you're holding out as your validation to do a pseudo holdout to estimate. The whole point of the validation thing is to estimate how it'll work on new data. What's the new data? The holdout. Yeah, this is a big concept. This is huge. I mean, this is, if you were to say I do predictive analytics and someone says, oh, what do you use for a holdout? And you're like, what's a holdout? And you're like, yeah, this is for k-fold, right? If we don't apply k-fold, we don't need a holdout. I would say you do. K-fold holdout is, if you're doing predictive analytics, Jinning, great question, 100 points, Jinning. K-fold is for validation, and you need validation. You can still have a holdout without validation, but validation will help you select the model to test on the holdout. You could technically not do a validation, but it does it for you. It's kind of like free. It's like free validation, and then you're like, I don't want it. You're like, wait, what? I mean, maybe computing power. That's a good argument. Maybe you don't have enough computing power. You could alter how the k-fold works, though. So I don't know. Yeah, no, great questions. Those are questions that make me think when you're like, like, how are they connected and things like this. Like, I can't tell you how many students, and I think I have a soft spot for the mathematics PhD people because it's like the math students have like taught me math and computer science. They'll come in with knowledge I don't have. And I had computer science students who are like, well, actually, Brian, I'm like, oh, well, tell me. They'll be like, actually, it's more like this. And I really like it when they correct the lingo and, go use their, because it's, and respect to all majors and all PhDs. It's just, sometimes the computer science and mathematics people know things, especially within my discipline, that I didn't even know. And hopefully it's going to be less of that. I say that, but I still want to learn more. But they have really deep understandings of some of these topics. And then I have understandings of things they don't, especially that's why I teach the class. So we're all here to help each other learn. Please ask deep questions or ask any questions you want, deep or not. You can be like, how's your day? It's a good day. It's a good day. So with this right here, I did figure something out this morning. Very quick aside. I swear the fastest hour in my life is the hour between when you wake up. Like I wake up an hour before class, and that hour just goes by like that. Like I make breakfast, I get ready, I get my Red Bull, and then I'm like, an hour just went by. It's like the quickest hour of my life. I know it's so quick. I don't know. There's a temporal distortion within that hour. It's just, I blink and I'm like, well, it's time to do class. I'm like, well, that was an hour. Okay, K-fold cross-validation, the one standard deviation rule. What are we talking about right here? What are we talking about? You guys know what I'm talking about, that fastest hour of your life. Okay, so one thing about the K-fold cross-validation process is that we're trying to estimate how it'll do on the holdout, but we typically underestimate. So a big thing right here is when you make your estimate of how it will do. See, for you guys, you can just turn on the computer, which I hope you guys like that. I think it's pretty cool. I kind of designed the class the way I want it to be. There's the K-fold. Oh, we've been talking about this. We know what's going on with this. Here's the biggest thing. Okay. A good question that was asked earlier was, where's that graphic? Here we go. A good question that was asked earlier was, do we always pick this model? And the answer is, meh. Your company, who knows, whatever, might say to you, we want a certain variable. So they might say, we need to put this variable in the model. So maybe you'll pick a model over here. Maybe you'll pick a model over here. Now, these models are nowhere near as good as the models over here, or estimated to be as good. But when it comes down to which model is better, we need some way to compare them. There's no perfect answer. So how are we going to compare these right here? And that just explains the dot on the far left, all that good stuff. So two models that are within one standard deviation. And first 1,000-point question of the day, I'm going to ask 3,000-point questions. First 1,000-point question of the day, if you use models that are within 68% of each other, or if you use models that are within one standard deviation of each other, you've basically built a what confidence interval. If you use models that are within one standard deviation, I did not do that on purpose, you're basically built a what percent confidence interval. Goes back in the day right here. Back to day 201. Boom, Andrew right there, 1,000 points, 68%. Yes. Sorry. I really did not do that on purpose. It's just when I hear 68, 95, 99.7, 68, 95, 99.7. So really what you're saying is these models, the differences to them, another 1,000 points, could be due to what? I'm hitting that button for a half second. They didn't get me last time. They're never going to catch me. The differences might be what? If these models, yeah, there we go. Random chance, Adam right there, 1,000 points, yeah. The difference is Adam was first person. Andrew's got his 1,000 for the day. Adam's got 1,000. The differences might be due to random chance. You can get up to 200, or you can break the rules and get the 1,000. One more person will get that today. Stay tuned to find out who. So why are we using this one standard deviation difference to say that, meh, between the models? Because you're saying you got model A, you got model B. It's like, I know it does, right? There's a lot of cohesion between the classes. And you'll notice that these topics blend together, that the confidence intervals are overlapping between them. So you're saying, well, maybe this model's the best, or maybe it's worse. Maybe this model over here, if you have overlapping confidence intervals, you're like, well, I don't know which one's better. You're like, I don't know. Maybe it's this model, maybe it's this model. The differences between them might just be due to random chance. Imagine if you run a 505 mile and your friend runs a 504 mile and your friend's like, ha, I told you I was better. Or if you go play basketball and you shoot 40 free throws and you make 30 and your friend makes 31, your friend's like, ha, I told you I was better at basketball. You're like, the differences between 30 free throws out of 40 and 31 out of 40 might just be due to random chance. How do you know you're better than me? How do you know that you're better than me when the differences we observed could be just due to random chance? We need to increase our sample size. I don't know. That's what we do in statistics. That's how we make decisions. So since these models have a variation or a difference between them that is so small in terms of a standardized metric, and that's why we use standard deviations, because they're standardized. This is a z-score of 1. We're back to z-scores again. A z-score of 1 is very, very tiny, so nothing going on. So what do we do? And this is, I thought this was here, and yesterday I was like, where's my standard deviations? We figure out the estimate for our models right here, and we figure out a standard deviation for it. So we have from our k-fold cross-validation process, where it's repeated k-folds, we have an estimate of how the model will do, and then we have an uncertainty. So once again, this sounds like 320 again, where we say we get our estimate of how the model will do. There's the mean, and then we have an uncertainty in this estimate. And what do we do? To make a 68% confidence interval, you go out 1 uncertainty. 95% confidence interval, you go out 2. We're just going to use 1 uncertainty because they'll start to really blend together if we do 2. You could say 2. You could use that. Could be your standard statistics, and you would just say, well, I use 2 to say all models within 2. I can't tell differences between the model. We just use 1 so we can kind of create more separation. We're being a little more lenient on saying there's differences. And there's just more process of it, so we can see more models right here. And we've just got the repeated k-fold. We should see the graphic here in a moment, which is going to be key. Where's my graphic? Really? Well, we can figure it out. This is on your homework assignment, though. When you're looking to see if models have differences, all you're going to do, this is key, write this down. You ready? This is the process. To see if 2 models are different, you are going to see what the typical miss for one model is and what the typical miss for another model is. You're just going to do that. You're going to take the differences and how they do. Does that make sense? You're going to take a difference and you're going to divide it by one of the 2 standard deviations. Which of the 2 for the last 1,000-point question of the day, you're going to look at which standard deviation for the models. You're only going to divide it by one of them. You're like, wait, there's 2 numbers here, Brian. There's 2 numbers. What standard deviation are you going to divide it by for the 2 models? You're going to take the difference between how the models do. That's all that is a difference. So you just find which of the 2 standard deviations. This is finding a z-score. The bigger one, Carolyn, 1,000 points right there. And Ahmed, Ahmed, you were first. You get 1,000 points for being first right there. So secret 1,000 right there. I like it, like peel first, or like I think I got it. This finds a z-score. So that's all this equation is. It's just observation or just a difference standardized. So you're just taking the difference and dividing it by a standard deviation, but you're taking the bigger one. And think about this. We're kind of, we're only doing 1 standard deviation, but we're going to take the bigger of the 2 standard deviations to kind of be more going towards, a bigger interval. So all you do, and this is for your homework, is you take the difference between the 2 models and you standardize it by the larger of the 2 standard deviations. And that'll turn it into a z-score. So are these 2 models different? Yes or no? Are these 2 models different? Yes or no? Are these 2 models different? Yes or no? That number right there, negative 1.4. Are these 2 models different? Yep. Jinning, 100 points right there. Great job. These 2 models are different, and I think we're using RMSE right now. So since we're estimating RMSE right here, we would take the model with the higher or lower RMSE. 100 points. Higher or lower RMSE, which model should be taken? RMSE is typical miss. Which model should be taken, the higher or lower RMSE? RMSE is typical miss the model makes. Lower. Yep. And you have to immediately know that RMSE you want to be lower. These are quick test questions I could ask. I'm already trying to figure out the final because you should know RMSE stands for typical miss. You want RMSE to be lower. So when you compare the 2 models, if there's a difference, you're going to select the model with the lower RMSE. So does everyone understand the process right here? When comparing 2 models, you will take how the models do on the data and use some sort of comparison metric. So we will compare the model's RMSEs, which here's the RMSE of, is that the mean? That's the mean. Here's the RMSE of the first model. Here's the RMSE of the second model. And this one has the lower RMSE. And that difference we observe after dividing by the larger of the 2 standard deviations is statistically significant. So the difference we observe between the 2 RMSEs right here, because these are RMSEs we're saying, is statistically significant. And we will thus select the one with the lower RMSE. If this was not statistically significant, we get into Occam's razor, one of my favorite things right here. So, and I'm going to make sure this has everything on here because I think it's missing one thing. I really need to update this slide on this. 2 explanations that have equal explanatory power, we should choose the simpler one. So when you look at it, that they have equal explanatory power, you should choose the simpler one. And usually it's that they have less assumptions, because you could say, okay, what should I, okay, I've got, uh, there was a glass on my table and it got knocked over. And so should my model be that the cat got out of its cage, jumped up on the table, and knocked off the glass? Or should I have the model that a ghost appeared and knocked off the glass? You're like, well, that's simpler. The ghost appeared and just knocked off the glass. That's so simple. But that would also have the underlying assumptions that ghosts exist and ghosts want to haunt you and ghosts like to knock glasses off tables. I think there's more assumptions in that model. They both have the same explanatory power, but that one requires more. Like, okay, we know you own a cat, and maybe you've seen your cat get out of the cage before. So you maybe you're like, okay, well, I do own a cat, and my cat has gotten out of the cage before, and I've seen it jump up on the table. I haven't seen the ghost appear in my apartment. Now, if you've seen the ghost appear, and that ghost is pointing at that glass, and it's like, yeah, I'm going to knock that glass off, then you're like, okay, that requires less assumptions. So they both kind of equal explanatory power. And so, yeah, so Occam's razor states that if two things have equal explanatory power, we use the one that has less assumptions. Not like that you can state quicker, but if you look at the underlying assumptions. So the way we use it in statistics is when you have two models that have equal explanatory power, we usually go to the simpler models. So we usually try to go to a model with less variables in it. Does that make sense? Like, why use a model with 100 variables if you could use a model with one variable? For an example like this, think about this. You can drive to New York by having 100 friends help you drive to New York, or you can drive to New York by having one friend drive you to New York. Now, you'll get there either way. And let's say it takes the same amount of time. It's going to take the same amount of time. You're just going to like jump out of a car and jump into the second one. Safely, of course. Uno. Solamente uno. Friend. How do I not know friend in Spanish? Amigo. There we go. Solamente uno amigo. Por su... How do I not know how to say car? I'm losing my Spanish. Got to practice. So, there we go. So I would just use one friend also. Solamente. I don't know why I keep saying that. It's because Andrew said it. So he got me on the Spanish kick right there. So we have right here that we'd obviously use one. It'd be much simpler. So think about this. They both have the same explanatory power. They both get you the same to New York, one friend versus, let's say, 5 friends, because they only have that many fingers. And so you would rather use the one friend, though, because equal explanatory power, simple model is going to be better. And how do we know that they are basically the same abilities? They're within one standard deviation. So we go for the simpler model rather than the complex model when we have this option. And once again, all models are wrong. All models are oversimplified, so they're completely wrong. For a simplified model to be good, certain assumptions must be true. So we need to make sure our assumptions work out. When tasked with predictive modeling, you must try out many algorithms, and dozens, if not hundreds, of particular models, if not thousands. The performance of each must be evaluated and must suit in the most suited algorithm and model for that specified problem needs to be identified. This is data mining. Data mining is trying out so many models that it would just, yeah. There's a thing we call the no free lunch theorem or theory, no free lunch, that you can't just use random forest models. People asked yesterday when I showed the models which one's best, and I was like, they're all good and they're all bad. Just depends. Just depends. The strategy for selecting a model right here, we might do a little quickly right here. But if you notice, once again, we're going to take our data immediately and we're going to put it to a training and a holdout. We saw that earlier when I drew the picture of basically the pizza sliced off with maybe 10, 15, 20, 25, 30%. And I mentioned yesterday, this won't be on the test, but Dr. Seaver likes to have 5 holdouts. And he does do consulting in industry, so he knows his stuff. So maybe we start doing 5 holdouts, but he wants to make sure it works. Why does he use his holdouts? To make sure what? Secret 1,000 points, you can get it even if you've gotten points. Why does he use 5 holdouts? He really wants to know it does this. Why is he using 5 holdouts? And I'm sure he has validation. He'd be like, of course I use validation. I'd be like, well, yeah, just wanted to ask. He'd be like, Brian, do you know stats? I'd be like, yeah. He'd be like, why are you asking me? Because you might not have enough data. Good question, Jordan. Jordan, you might get the secret 1,000. And why is he using 5 holdouts? He wants to really make sure it does what? When he uses 5 holdouts, he's really ensuring that it does what? So he'd have 5 separate holdouts to make sure it does this. More specifically, you are correct, Andrew, but more specifically. Boom, Jordan right there. Yep. Works on new data. That's the whole point of the holdouts, to make sure, or hold out, to work on new data, or hold outs. Generalizes to new data. Yep. So be very specific that the model generalizes to new data. The idea, and generalize right there. Yeah, Caroline, that's right. I mean, that's the idea of generalization. The model generalizes, it works on new data. That is literally what generalize means. And then we have the estimated generalization error from the validation. Now, how do we know if it works pretty well on new data? A good model should not have the error on the holdout sample to be much larger than the estimated from the k-fold cross-validation. So how much is too much? When you make your estimate right here, let's take a look. We've got to go way back in time right here. This model was predicted to have an error of, let's say, 3.9. Does everyone see why? Sure, we'll say 3.9. Does everyone see this model was estimated to have an error of 3.9? Now round it, it had an error of about what? So it was estimated to be about 3.9. And then it was actually about what on the holdout? The model actually had an error very close to what? It was estimated to be about 3.9. And it actually had an error of what? Yep. That's exactly. And so what do? Here's the mathematics. Write this down. You take what it did on the holdout. So you take what it did on the holdout and you divide by what you expected it to do, and there it is. Is this model doing about what we expected? Is it overfit or not so overfit? You have to look at this portion of it right there. Because if it was 1, it would have done exactly what we expected. Like we're looking at a ratio of how it does on the holdout versus the train. So let me write this. Holdout over train. And if you want, you could do 1 minus, whatever, no. Holdout divided by train minus 1. You could, let me see. Let me retract that message. Okay. Holdout divided by train, and then minus 1. Don't want anyone to do minus 1 on the train. So you're looking at, and that'll get you the percentage. So if I take this number here, which I'm talking about, whoops, I'm in the chat. Wrong screen. So if I were to take this number right here, and I do this number, sure, gotta type it down, 1.073 or something minus 1. That's the percent increase. We're looking for z-scores below. So this is not a z-score. This is a ratio. Good question, Jordan. So the math I just put in the chat, that won't get you a z-score. That'll get you the ratio of how well your model did on the holdout versus the train. And what is the interpretation of this number right here? This model, let me highlight it and bring the number back on the screen. What is the interpretation of this number? This is key. Jordan, great questions. What is the interpretation of that number? What does that mean? That it's 7.3%, because it's a ratio. It's 7.3%. What does that mean? That my model, I'll fill in more words. My model did 7.3%. Not yet. Good guess, Adam. 100 points. Good guess, Adam. My model did 7.3% than it did on the kind of. Andrew, that's kind of right. So, but fill in more words. My model did 7.3% worse than on the. Not better. My model did 7.3% worse on the than it did on the than I expected it to do, you could say also. My model did 7.3% worse on the holdout than we would have expected it to do via the validation portion. Does that make sense? Let's look at just the way this is calculated, because here is the validation. So the number 3.9 was taken from the estimate, and then the number 4.2 was taken from how it actually did. So it did 7.3% worse on the holdout than we estimated from the validation. So is this model overfit by way of the slides? Is this model, too many slides. Is this model overfit using this right here? Is that model overfit or it does about what we expect? Like, meh. It was 7.3% worse. Is this kind of okay or no, big problem? It works. Nitin, 100 points right there. You're right. It works. It's fine. It's good. That's about what we expect. 10% is kind of bad. 20% is very bad. So there's no point at which your model's overfit. It's just more overfit. All models are wrong. We keep saying that. So there's no, like, your model's probably going to do worse on it. It could do better. It's possible. I see it. It happens. And we do see it in the graphic also that the models that were below the line were the ones that were doing better than we expected them to do via the estimate. It's if you look, maybe it's like, I don't know, like how many models are here? Maybe 500. So maybe that's like 2-3%. So there are models that do better on the estimated. Is that correct? Because these models are doing worse. Here's the estimate. This one was estimated to have an error of 4.3, and it actually had an error of this. That's doing worse, isn't it? Oh, no, my brain's just breaking today. And this model was estimated, because there's the estimate, and there's how it actually did. So you can look right there, and you can see how it's working. So, it did better on the holdout. Yeah, that's what I wanted to say. It did better on the holdout, which we don't usually see. This model right here did better. These models are doing better on the holdout, because if you look, they were estimated to work around 4.3, and then they actually worked around 4.2. Does that make sense, everybody? These models were estimated to have an error of 4.3, but then they actually had an error of 4.2. They're working better on the holdout. So those are not overfit at all. Those are actually working better than we thought they would. But it's not that often you get models that work better. It's more often that the models work worse. So every single model above the line is working worse. Like this model, you were like, this model will have an error of about 4.46, and then it had an error of 4.9. That is one of our worst overfit models right here. The model did way worse on the holdout than we thought it would do. So that is a key concept right there, the idea of overfitting. We can tell usually by the ratio of how it does on the holdout versus how it does on the validation. So holdout over validation gets you the ratio of how it does on the holdout versus the validation, i.e. you divide them, and then we want to see no more than about a 10% increase. And I put the equations in the chat to show you how to get that. So the last thing right here, that's okay, it was about 10% higher. If you have a big problem with this, switch your models, toss your model. If your model's overfit, you want to switch. If that occurs to you, make sure you wait. If out of curiosity, you make predictions on the holdout sample using a different model and find its error is lower than the... Oh, yeah. So this right here, okay, this is what happens. This is the instance of your model doing better on the holdout, which can happen. I was slightly confused. We did mention this, that your model can do better on the holdout. That's not a problem. It means your model did better. So don't think because they're off, there's a problem. Look to see if your model does worse on the holdout. Overfitting is when your model does not generalize and your estimate is way lower than how it actually works on the holdout. So the problem with overfitting is when you have a low validation and a high holdout error. But it's not a problem when you have a holdout that is below your validation. That just means for some reason your model works better on new data than you thought it would. So that's key right there. And they just say right here, the key things. Here we go into the last big topic for this set of slides. We will get to another set of slides here coming up soon, but we have the generalization error and the bias variance trade-off. This is huge. We only have a few more slides in this, but these are big topics. So the mean squared error is going to be our expected generalization error, which has two key components. There's the irreducible bias, which we really can't control for. But the two key components, when we're talking about how does our model generalize, are going to be the bias of the model and the variance of the model. Now, here's the thing. Man, I gotta see this. Can't talk between the transitions, you won't hear me. When I first started doing statistics, I thought to myself, why not just put every variable in the model? So we can kind of see this right now. We could do this. Yeah, let's do this. So if we were to do this, let's make a model right here and see a problem. This is Brian 2000 Brian, 2000, 2001 Brian. He would say, let's do this. Let's go here. Let's pull data, survey 10. We're just pulling up a data frame that's inside of reg class. So let's go here to library reg class. And so there's the library. I already had it loaded, so I could do that. We're going to go here to train, and let's do it the way it's in the notes. Train.rows. So I'm going to store an element train.rows, and I'm going to go to sample, and I'm going to sample 1 through the number of rows that are in survey 10, and I'm going to sample 70% of them. I think this will do it. I think it's the right way. And train.rows should have 70%. Train.rows is empty. And why is my brain not working today? Oh, ha 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 ha. Times n row survey 10. There we go. Now it has 70% of the rows. So I created just a numeric vector which randomly chose. And if I want to make these results replicatable, I could go here to set.seed. What? Stop being weird today. Set.seed, and we'll go 474. Just we're using that as the name of our class. Now if someone runs this, they'll get the same thing. And now we're going to go here. We're going to go to train, and we're going to go to survey 10. And we're only going to select in survey 10 the train rows. And that'll create the train rows. And now we go here to survey 10, and we make our holdout. And what's the only thing that's going to change right here? 1,000-point question. Who's paying attention? What's the only thing that's going to change right here when I do this? Quick, who's got it? You can get it on top of the points you've been getting today. Big, crazy points today. Be paying attention. Boom, Jordan right there. You got it. That's it. We got it. We got our train. We got our holdout. Now, the first thing I'm going to do is I'm going to look at the train and the holdout, and I'm going to make sure it looks the way I want it to look. 210, 20 variables. 49, 20 variables. Please, 100 points, everyone else. Great. Thank you, everyone, for following along right there. I need to do more like 100-point questions for everyone. I'll do more of those here in a moment. But we have here the holdout has 210 and has 20. This has 49 and 20. It's a subset of these. I like that, Andrew. So now what I'm going to do is I'm going to make a linear model stored into an object. And I'm going to make, I wonder how this is going to work. I'm interested. I'm going to predict people's weights right here. Why not? Let's predict people's weights, tilde, dot, squared, second. I think this will work. Hopefully it doesn't break everything. Data equals train. Cool. Now we're going to make a summary to see how well we explain people's weights. And we have 91% of the variation with a residual standard error of 14 pounds. So if I could use this model, I'd use this model to predict somebody's weight, and it would typically be off by about 14 pounds. Pretty good model right there. So we now have this model stored, and guess what we can do with this model? We can go here, and I think this should work. Let's take, and I think this will work. Cross your fingers, everybody. Let's go here and go to predict with the model. So you can predict with the model. It'll predict on its own data. But let's say new data equals holdout. Warning, that's fine. Predictions from rank deficient, I don't mind. Do you want to show me a warning? I don't want to see warnings. I want to go to suppress warnings. Suppress warnings, amazing thing when you don't want to read. Rank deficient just means there's a problem with the variables a little bit, but I was thinking we might get some sort of error. So what did I just get from my model? These are all, let's put a note on it, y hats, because these are all predicteds. Y hats, i.e. predicteds. So these are all predicted values. The multiple r squared is the r squared. It's the percent of variation y explained by the variation in the x's. So 91% of the variation in somebody's weight is explained by my model. Great question, Anisha. 1,000 points. Thank you for asking. Totally mean it. If you see something you don't know, ask it. The multiple r squared is just r squared. It calls it multiple r squared. So it's the percent of variation in y explained by the variation in x's because there's multiple x's. Yep. Ask anything you don't know in the output. That's a key thing I always want people to do. When you see something, ask it. This right here is adjusted for how many variables in the model. So this is the r squared adjusted for the amount of variables that are in the model, and it'll always be lower because it's r squared with a penalty term. So we penalize ourselves for adding more variables. I'll be very interested to see if this works. Let's call these predictions right here. And that is our predictions. And guess what we're going to do here? We're going to go to the holdout. And on the holdout, we're going to go to people's, we're predicting their weight, right? And then we're going to subtract predictions. Guess what all those are? And that's a bad one right there. All of these are whats? All of these are whats. Every single one of these is a what right now. Every single one of these. I didn't really make a validation portion. These are errors. Yep. So what am I going to do? The errors. I'm going to what the errors. I'm going to what my errors. 100 points. Keep answering. Jordan, 100 points. You get to, if you get the secret 1,000, you can get up to 1,200 a day. I'm going to do what to my errors. 100 points. Keep answering. What are we going to do to the errors to get the RMSE? I'm going to find RMSE right now. What am I going to do to the errors to get the RMSEs? Hint, root mean square error. Not scale them. RMSE, root mean squared ginning. Yep, square them. Square them. There's the squared error. Now we need to take the mean. So here's the mean of the, there's the mean and square root. There's the root mean squared error. And there. Whoa, no, wait a minute. No way. Did I do this right? Oh, what? No way. Did I do this right? Did I not square it properly? Let me make sure this was squared. Let me do this. I think I didn't do it. There we go. You know what I could do? I knew there was a problem. I was like, that is not right. I was like, I wanted this example to not work. And I was like, that shouldn't work like that. Let me, I see what happened mathematically. So let's go here and go to squared error. And we're just going to store the squared error into here. And then we're going to go square root of the mean of the squared error. And there's it right there. So there was, I was taking the mean and then squaring it. And I wasn't doing the root mean of the squared error. And so now let's compare this number here. There's it on the holdout to this number. Come on. There we go. This number here. Is this overfit? That is very overfit. Oh yeah, double click anything and then you can just put a parentheses around it. So if you double click something and it's highlighted, you can just do an open parentheses. Adam, 1,000 points. Thank you for asking. No, yeah, great job. You only get the 1,000 one time, but you might have got it right there. Trying to throw out thousands to people, like the questions. You just highlight something and then you do an open parentheses. You can highlight something and do a quote and it'll quote it. You can highlight something and do a bracket and it'll bracket it. You can do any sort of thing around it. You might be able to star it. Oh, you can't star it. Can't do that though. So give it a shot. Good thing to know. Helps out a lot with doing quick coding, just to like triple click something. So you could always triple click something and put parentheses around it like that. I hate that it goes to the new line though. It's always been, I think if we don't have a new line selected, we can triple click. And yeah, as long as you're on the last line, it won't go to a new line. So that's, I've used that trick before. More tricks you learn, the quicker you get at coding. I'm here to teach you those tricks. This is 100% totally overfit. Actually, it's 170% overfit. We could take this right here and show that this is crazily overfit. This is ridiculously overfit right here. 170% worse on the holdout than it is. And so what have we done? We've made a model with extremely low bias. By adding in so many variables into this model, we made a very low bias model. But watch this. Let's change what we have going on right here, and let's make this model this. This, error in terms, did not like that. Don't know. Oh, is it not going to? Oh, 0.1. Sorry. It should work with 1. Okay, so now it made the model. Good. Now the residual, whoa, it's actually very similar. Our model that we tested on the holdout like did as worse on the holdout as the naive model. And the naive model, take this note, is going to predict the mean of people's weights for the data it was trained on. So this model, 155, is predicting the mean weight for people because all it has is the intercept. There's no X variables. Does everyone see this? And you should have these key notes that this is the naive model and it's predicting the mean weight of people. And that's what its prediction is. So let's say a person is male and they're 6'3" and they're 38 years old. What's this model going to predict their weight? What's this model predict a 38-year-old male who's 6'3"? What's it predict their weight? Any ideas? 100 points? Who knows? What's it predict their weight? They're male, they're 6'3", they're 38 years old. What's it predict? 155. Yeah. How about a female? Female. They're 5'3". They're 20 years old. What's it predict for the female who's 5'3", 20 years old? They're senior in college. Wait, they're 20. Sure, they're senior. 155. Yeah, predicts 155. What's it predict for a newborn baby? What's it predict for a newborn baby? What's it predict for a newborn baby? What's it predict? 155. Now, this model is probably not made from that kind of data. So this model, that'd be an extrapolation because this model was not created from that data. But it doesn't matter what I say. It doesn't matter what, there's no X's. Does everyone see there's, exactly. There's no X's. There's no X's in this model. This model predicts the same thing no matter what the X's are. So this is the jumping point. This is the naive model. If you remember from 320, we talked about the naive model. It's going to predict the same thing. It's going to, there's no X's. So let's actually use the naive model to make predictions on the holdout. Let's get that squared error. And then, wow, you know what's interesting here is the holdout. There's the holdout. And then let's go grab the error from this. Whoa. It's almost like it works almost exactly what on the holdout as it did on the training data. This model worked nearly what? So this model here that had an error of 36, nearly the same, virtually identical. So now we just made a model that has extremely high bias, but very low variance. And you might start to understand what variance is by this. This model that was so simple had a very high bias, which means the error was very large. This model right here, let me point to it. Here, this model had high bias. It did a poor job of explaining weight, but when we brought it to new data, it worked nearly identical. Does that make sense? That it had like very little variance. That when we bring it to new data, it works nearly identical to how it worked. Now, it's really bad, but it does the same sort of bad. But it's way too high bias. It works so bad, but hey, it works the same bad on new data. The other model was so great. It was like, whoa, this model here is amazing. It's 16 pounds, 91% of the variation. Why did the R squared change? I swear it was 91% last time I looked at it. Oh, I did squared terms. Haha. Because I really wanted it overfit. I did squared terms. There we go. So there's, because I overfitted even more, I did all the squared of the variables. So this model here was the very low what? This model, because it fits so well, is very low what? This model fits the data really, 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 really well. It's very low what? For the data it was created from, it has very low what? Has very low what? This model with all these variables, it's got all these variables, very low bias. And bias is like how well it works on the data it was created from. It has very low bias. And then variance, this model has very high variance because, and we could just take, I could store the RMSE in here. It's way worse. And there, this was it right here. This was the equation we did for the variance of it. The variance of it was ridiculous. It works horribly on new data. And so what hurts variance? Think of it like this. Variance is hurt by taking more information. This is so counterintuitive. The more information you take from your data, the more you'll learn your data and the better you'll do on it. What am I talking about? The more information you take from your data, the better you'll learn on it and the better you'll do on it. I'm talking about having a lower what? The more information you take from your data, the better you'll learn on it and the lower this will be when you try to explain your data, your data that you're making your model from. I'm talking about you'll have a lower, you'll miss smaller amounts on it. You'll have a smaller miss on it. You'll have a smaller miss on it. Your misses will be smaller. You'll do better on it. Your typical misses will be smaller. RMSE bias. And RMSE is your bias right here. Great job right there. It's the RMSE, it's the bias. Your model will do better on the data it was created from. It will have smaller typical misses because you're extracting more information, you're learning more. But as you learn more on your original data, as you take more information, this is the counterintuitive thing. Your model will become dependent on that data. It's like your model's like, I need that data. That data is what created me. So if you give it a bunch of like variables, your model will start to fit to those variables. And if you give it too many variables, you will overfit and you'll have high variance. The more variables you put into your model, the more you risk having a high variance model, which is a model that works well on the data it was created from, but does not work well on new data, the holdout, because you've overlearned your original data. You've extracted too much information. So it's like imagine this. Here's a perfect example. I wish Julio was here. I was always talking about Julio. Julio's amazing. So if Julio is trying to teach somebody he's an outfielder coach. So if he's trying to teach someone, I think he's outfielder. He was in Major League, but I think he coaches outfield now. He coaches a lot of things. Anyways, enough. If he's trying to teach somebody how to play baseball, what should he do? Like, what would be a better idea with the outfield? For him to say, okay, the first thing you want to do is make an estimate, like you should watch the ball get hit and then make an estimate of where it's going to land. Immediately start sprinting to that spot and then keep the sun out of your eyes. Or should he say, you need to, I'm just trying to think of an overfit model. I wish I knew more about baseball. You need to immediately figure out the speed and trajectory of which the ball is hit, and then you need to sprint for 20% of the time and jog for the remaining 80% of the time, and then stretch your arms as you run. It sounds like he might just be, at this point, it might sound like he's fitting the model for how maybe he catches the ball, because he's like the training data. Does that make sense? Like how he catches the ball is kind of like a training set of how people catch the ball. And this probably works excellent for him. But if you're a coach, you want to give models that work what? Not for you, the model that was trained on. You want to give models that work on what? If you're the coach, you don't want to say exactly what works for you. Like, you don't want to be like, this is exactly what works for me. Because then you might be overfitting for what you do. You want to give models that work well on what? No one knows. It's what the holdout is. Work for the future, work for new data, work for other players. So he's going to use the model that works for him and maybe use a simpler version, or like he's going to go for the most important things. Think about this. If you're giving a coaching technique, if you're coaching somebody, you're going to go for the most important things first. And then you're not going to go to the things like, okay, be stretching your arms while you're running, like get your arm ready. I mean, you're going to eventually maybe get to those things. I'm sure there's things that are important like that, but you're going to go for the most important things, and you're going to try to keep the model as simple as possible. And then you're going to work on the smaller things after you get the bigger things done. You're always going to go probably for the bigger things and then get the small things done later on. And watch if someone will be like, no, you get the little things done to make sure you have I don't know. This is how statistics works, though, and translating it into an idea. Okay. So now I just toss him in the deep and see what he does. The goal is to win the game rather than to win the world. Yeah, exactly. And so the bias and the variance are going to have a trade-off here. Oh, let's hop to the other screen. So we've got definitions of what these are. Irreducible complexity, we don't really worry about much. For instance, no matter what model we make for predicting a coin, it's always going to have a 50% error. Irreducible error, you can just not get rid of. I don't like putting this on the test. Maybe if I did, it would just be error your model can't. It'd be like if we're predicting people's weights, there's no way to get less than a 4%, be off by less than 4 pounds. It's just like there's no way to fix the model. So we don't really worry about the irreducible. We care about the bias, we care about the variance, and we have to know what those are very much. Bias goes to just how well our model goes at predicting the data, and variance is related to how much information we are extracting from our data. Models that extract more information, have more variables, will have higher variance. Models that extract more information, have more variables, will have lower bias. So a high bias model would be the naive model. The naive model makes really bad predictions because it doesn't have any X's. But the naive model has very low variance because it doesn't extract information. The squared model with all the variables has very low bias because it's taking all this information and making really good predictions, but then it has very high variance because it's extracting a ton of information and overfitting to the training data, and it doesn't work on new data. Key that we know exactly what bias and variance are. So which of these right here, we're trying to fit something to a circle. Which of these right here, I don't like the way this graphic is on the new slides. Which of these would have the, don't we have another one? Sure, I like this better. Okay, so which of these models, going from the line to the green bendy spline, so this one right here that's dipping is the green bendy one. So that's the green bendy one. Which of these is going to be the lowest variance, the line or the green bendy model? See, this is a perfect slide. It's like, which model, 1, 2, 5, or 8 is the, I don't remember what I said. Whatever the answer people put. Then I'll be like, yes, that's the blank blank. The green bendy one's going to have what? That's what I'm talking about. Low this, high this. Okay, so if we're saying line, the line is going to have the lowest variance, the highest bias. The line does the worst on the data, but if we were to do it on a new data set, the line would do virtually identical. I feel like we removed some slides that I really like. So the line on new data would do about the same. There we go. Here's the slides I was looking for. So on new data, the line would do about the same, but it has worse error. But look, these black lines are new lines fit to data, like holdouts. So the line given different data sets, and sorry, I missaid something. These new lines are theoretically, if we had different data, the lines we would get. And look at the variance in the lines. The variance in the lines, theoretically, if we had different data, would be virtually identical. These are virtually identical lines, but the bendy ones, how different do these look given different theoretical training sets? Given different theoretical training datas, how different are these models here? Given different theoretical training data, how different are these? How different are these given different theoretical data sets? Extremely. And these are low bias, yeah, because they're going to fit the data they're made for, but we're extracting so much information that we're overfitting it and we're over-learning the data. Does this make sense what bias and variance is? These are low bias models, but they're high variance because they're dependent on the data they're created from. We're extracting so much information out of them. But here, these models have more bias because they don't go through the points as well, but they're going to be virtually identical, so they're going to have low variance. So you have to find, I just want to show the graphic that shows the sweet spot for it. You have to find this sweet spot between getting enough, this is bias going down, so here's as you're adding variables, and then this is the right point. Where's the right point? We'll let the k-fold cross-validation kind of figure these things out because we're going to get an estimate of how to work on new data. So the k-fold cross-validation process is going to help us not overfit. It's going to help us pick the right amount of variables or the right parameters in our model, which is going to be so huge. We've seen it yesterday, but this is the whole goal of it. What is the most underfit model? I'll tell you a perfect test question. Let's do this. Wrong button. Right button. Yep. Okay, so here's a really good way to write a test question. I'm almost putting this for myself in here as a reminder. Which of these models is going to be, and we'd mix them up here, but which of these models is going to be the most you should know this, like what all these mean. Which of these models, A, B, this is a perfect test question, C, and they'd be mixed up. Which of these models is the most overfit? Did I say overfit or did I say underfit? Sorry, this is my brain getting back on track. It's at the start of the class. I have the most knowledge. D is going to be a model that has the highest amount of bias, but the lowest variance. D is the most underfit model because it's the naive model. D and A would be overfit. A is, nice job, Anisha, right there. A is the most overfit, it has the most variables, and it'll have the lowest bias. It'll have the highest variance. So given a different set of training data, it would come to a completely different model. So because it's going to make all these different estimates for all these different X's, and it's going to have high variance from training set to training set. So theoretically speaking, a different training set would make a vastly different model because we're extracting so much information. And so A is the most overfit. That's pretty overfit, and that's a little bit underfit. Is a decent model, predicting someone's weight from their height. Like the best model from this is probably this. If I had to pick a model, I'd probably pick, it's a pretty simple model. We'll let, the k-fold cross-validation process tell us which models are the best. But this is, going on a scale. Now I'd have them mixed up on the test. And you have to know that this is all the variables squared. This is all the variables. This is a single variable. This is the naive model. It has a special notation for the naive model. So I can't stress that enough that y tilde 1 is the naive model. So if you ever have to build the naive, you just do that, and it fits the intercept of the model. Key things we should know. I think that does it for this slides, and we've done a little bit of numeric prediction today. Let's go right here. The one standard deviation rule, so I think we are going to get to see the graphic that I've been just hoping all lecture we'll get to see, is we pick the models within one standard deviation, and it's not here. So once again, we do this. It's impossible to determine whether or not a model is overfit by looking at its performance on the training data, by looking at the estimated k-fold. Yeah. So what we do right here, we select the model with the lowest estimated generalization or expected, and then we can select models within one standard deviation. These are the things we've been repeating endlessly throughout this lecture. We do not want to underfit. We do not want to overfit. Underfitting is going to have very high bias, and overfitting is going to have very low bias. So when you see overfit, it's like your model did super well on the data it's created from, and that's like the squared to the second. When you see underfit, your model where's the high bias, that means you have a model that works really bad on the data it was created from. You could have done a lot better. This is more like the naive model. So the naive model is the most underfit model we can make, and the most overfit model we can make is just throwing in tons of variables. Maybe that's the answer. Maybe it's good. Only the k-fold cross-validation will find out. Who feels pretty good about this chapter? I feel like this is a lot of, we repeat the same thing. It all merges together. I feel like this is maybe one of the easiest chapters to completely understand. You just have key terms which are listed. We're going to start this one up today here. Yep. If you think we're in the last 2 weeks, and what happens is, if you look at this is March 01, which means spring break was about to hit, and then yes, this is it. We're tracking really well because this is the last 2 weeks, and this is right before spring break. So let's do this. Let's do some numeric predictions with linear regression. So here we go. Let's do this. Numeric predictions with linear regression. Nice. Could you say once more about the optimal model? Oh, that's Anisha, great question. The optimal model that we pick, we need to have some sort of metric to look at no matter what we're doing. And so we're going to do linear here in a moment. You got to way back. We need to have some sort of measure to look at. If we're doing regression, which we're about to do, we're going to look at RMSE, and then we'll pick our model based on how we think it will do, which is the validation portion. Our goal is to pick the model on the validation portion and then test it out on the holdout. And it'll run all the code for us to make the models. It'll make all these models for us, and then we can look through the list of models and we can make our selection. The output for this looks so awesome. Like, I should just make some for you. Well, why not? I'll show a little output for you because it looks so cool. Okay. So remember, I put those most important slides at the very top so we would know where our slides are at. And here it is right here, I think. And let's go ahead and take a look at one of these models. So I need to make my TR control, right? That's where that one's at. My brain is not fit control. I need to make my fit control. The fit controls are all stored for you. Where's the fit controls at? Where's the first mention of them? Lots of notes. Here we go. Okay. This is a very important part of this right here, because please notice right here, this is regression and this is classification. We should know instantaneously that regression is for a what variable? It's for a quantitative y, and we'll just copy this right here. Well, sure, why not? And this is so key. You have to know right here that you are doing quantitative wise up here or you're doing categorical down below. So please note that there's a change where it's class probs equals true, and this will fit on accuracy, and this one down here will do AUC ROC. So you've got here your k-fold cross-validation, and you've got here your repeated k-folds, and then down here you're doing still k-fold cross-validation. Probably do repeated, but down here just the fit. So you could change and do method. You could do repeated CV and then do repeats. So everything right here should probably work. I'm just going to move these to this, and then I'm going to go here, and I'm going to type repeats. And I hate when the autocomplete doesn't. It should do this. Repeats 10, comma, and it should accept this. Could not find train control. That's because caret's not on. So without caret, we didn't have that. And now we should, and it runs. So I've just made a, which isn't even in the notes, but you can do repeated cross-validation with this. But this is if I'm predicting a categorical. You need to know the difference here. This is predicting categorical, and it's fit to accuracy. So once again, if you look at the notes, as we say, you could fit on accuracy, or you can fit on this. Misclassification and accuracy are just complements. So you're like, why can't I fit on misclassification? Well, that's the complement of accuracy. They're just either you get something right or you get it wrong. We don't fit on R squared. There might be a way. I don't know it. And I bet there's a way to fit on MAE. We just don't do that. Caret fits on RMSE, at least the way I use it. So you notice up here, these up here, there we go. These right up here are going to fit on RMSE. So everything up here is fitting on RMSE because it's regression, and everything down below here is fitting on some sort of categorical metric like accuracy. And once again, you see accuracy and AUC, which once again are on these slides right here. So we usually just fit on one of these two things right here. You can fit on kappa, but I don't like kappa. I don't know. It's personal preference. And so I'm going to do a quantitative model right here. And let's go here to support vector machine. Not support vector machine. Let's go here to, why can't I think of the name of it? It's lasso and ridge put together. It's not grid. It's not span grid. Why can't I think of the name of it? It's lasso and ridge put together. It's elastic net regression. There we go, elastic net. So do we call it elastic net in here? So it's got an alpha. There we go. And so, oh, it's, why can't I think of the name of it? I should have had more breakfast. Well, here we go. It's right here. There we go. It's GLM net. It's GLM net. So there it is, GLM net. There it is. And you'll notice the method right here is GLM net. Just couldn't think. Regularized, there it is. And regularized means it's fit to that. Couldn't think of the code. Lots of codes you got to memorize in your head. Lots of little things. You got to know how they work. Okay. So here's the code right here that we're going to focus on for this chapter. Kind of a good introduction to it so we can see what's going on. And this is a regression right here. And we need to know what the expand grid is. Now, we covered this yesterday. Remember when we were baking cakes yesterday? Does anyone remember us baking cakes yesterday? And we were making all the different cakes we could make. A really good test question for this would be how many different models are we testing? How many different models will I be testing? And this will be, we will get to this by the end of tomorrow, but this is an introduction to what we're going to be doing. How many different models am I testing right here? Here's a good way to look at it. There are two tuning parameters. The tuning parameters are the knobs you can turn to change your model. So how many different models am I testing? It's very easy to check if you just run the code and look at the expand grid, but we should be able to break this down. Alpha will be a number going from 0 to 1 by 0.25. So 0, 0.25, 0.5, 0.75, 5. That's close chaining. I'll explain. So look at alpha right here. Come on, R. Don't be so crazy. Alpha are these numbers. How many numbers of alpha are there? How many numbers? There are 5. 100 points starting. We got this. It's almost Friday. Not today, though. So there's 5 alpha levels. How many levels of lambda are there? Lambda is 10 raised to the sequence of -4 going by, -4 to 1 going by 0.5. So it'll be 10 raised to the -4, -3.5, -3, -2.5, -2, -1.5, -1. 7 numbers. So we should get 7 numbers here. Let's take a look at it. And let's just look at lambda. 1, 2, 3, 4, 5, 6, 7. Does everyone see? It's 10 raised to the sequence of these numbers. Jinning, 1,000 points. You're right. Yep. That's exactly what we did yesterday. Yep. That's exactly what I wanted you to see. Those are all the combinations. That was the baking of the cake example yesterday where we did all the combinations that these can be together. So we're going to do all the combinations of these. Does that make sense? You just saw it right there. You saw it perfectly. Well earned. If you got 1,000 already, you're at 2,000. Exactly what I wanted you to see. That there are 5 ways we're going to let alpha be. Alpha has 5 options. Lambda has 7 options. There's a total of 35. I put questions like this on the test. If you don't know how to do it, it seems impossible. But you just have to figure out how many values of alpha are there, how many values of lambda, and you just multiply them together. Do you want that question on the test? Question just like this? Sometimes I make it easier. You can make it easier if you go here and you just go to the following. This makes it way easier, but still you have to know how to do it. So this right here, sure, we'll do. This right here would have 12 combinations because it's 3 times that. And I could add in another variable. There's not another one for this, but if there was, you could add in Brian equals, and I'm going to call this expand grid 2. Brian equals 1, 2, 3, 4. So this is 3 times 4 times 3. So this is 36. I'm not going to overwrite my original expand grid, but this will have 36. How did I know there's 36? Because 3 times 4 times 2. So once again, the mathematics on this is 3 times 4 times 3. I think I said 2 by accident a second ago, but there's 3 levels to Brian. If I add in another variable, quick 1,000-point question, Darren equals 1, 2. How many levels to expand grid 2 are there now? Whoops, break the code. How many levels to expand grid 2? Quick 1,000-point question. Who knows? You can get the double. You can get the bonus double. Who knows? Right here. How many levels to expand grid 2 now? How many combinations are there in expand grid 2? Use this and use that. Who knows? See if you can get this. So this was it originally, and then I did this to it. How many levels when I run expand grid 2? Boom, Ahmed right there. You're right. Yep. 72. Because it's going, this is the thing, is that as you, it's how many there ever were, and now it's doing, because think about this, if you look at it, the way it permutates it, it just ran all the original combinations, and then it changed Darren to level 2 and ran all the combinations again. Does it make sense how it's making all these combinations? It's literally just doing every combination just by permutating 0.51, 0.51, and then it moves this one over. And then when it gets done moving this one through, it starts it over and goes to the next of this. And so by adding Darren here, it just did everything again, but did it with Darren at level 2. Does that make sense what this is doing, how this code just permutates all these combinations to make all possible combinations? And all possible combinations of them is just how many there are for each one times each one. So you just do 3 times 4 times 3 times 2. So if you notice, as your expand grid grows, you'll make a lot of models. Now I want to reverse time here because we don't want that looking like that. That'll not run for the code. It looks more complicated when it's a sequence because you'd have to figure out how many things are in the sequence. So if you know there's 3 things in this sequence and there's 4 things in this sequence, I think that's my original expand grid. And I think it was 12, wasn't it? It was 35, right? Because 5 times 7. Jennings said that. It's 5 times 7. So now, let me make sure we have the right data loaded up. Oh, we need the train data. Where is the train data? What data did we train this on? I can make, see lots of good stuff here. It's showing you how all the code works. When they came into the chat yesterday and they were like, this is your thing that you need to know, they were being serious. So here we go. I don't know why it's commented out. Here's splitting your data into training and holdouts. Data not found. Oh, because we want it to be called data. What shall we predict? So what shall we predict? Let's do what were we doing before? We were doing weight, right? We were predicting people's weights. So let's go survey 10 and let's go here and we're going to call this data and we're going to call it survey 10. So the reason I called it that is because now I can just run these codes and now that made my training and my holdout. And we're good on that. Note on discrete and combining levels. So we're not doing that one. We're just making 80% right there. So now we have our trained data. Let's go back down to the code right here. And we have our alpha, we have our lambda. More on those, especially tomorrow. So now we're going to go here. is data called data. It's called train. Because we're using train, of course. This is huge. I almost made a mistake because I'm just going quickly for a moment. Do not put your data here. Put your train data. Training data creates your model. That's where your training data goes. So now I'm just going to go here to predict weight. And this should work because that's my y variable. It's in my train. Should work. Does work. Don't know why it wouldn't work. I was afraid it wouldn't. Sometimes things don't work. And now we're going to plot out to see which model to use. Cool. Here's the model we should use. It looks like, the regularization parameter, which regularization will, I need to vanish. So the model we're going to use is going to have a regularization of 0.1. You know what I'm actually going to do is I'm actually going to expand grid out further on this. I'm going to add into my expand grid another, and that's the regularization is the lambda. So I want to add to this lambda right here another value, because if we go to negative and we go to positive, so I want to bring this to, let me bring it to this right here and make it finer. Okay, this will take a moment longer. What's going to happen now is there are going to be more dots over here. There's going to be more dots on the regularization. So let's see this right here and see what we get. It's going to take longer to run. Didn't take too long. And there we go. Cool. Now we got a better spot. What did I want to see? I wanted to see what's going on better right here. What do we want our RMSE to be? We want our RMSE to be as small as possible. And if you notice here, there's a mixing percentage. And it looks like we want to mix at 1. This controls the alpha. More on that later. And we want our RMSE to be low. Great job, Anisha, right there. Another 100 points. We want our RMSE to be low. So if you notice here, this is a mixing, an alpha of 1. This is your alpha right here. And we want a regularization that's about in the middle. So you can easily go here to the best model we've created. We're just going to go here and look at the best model. And it has an alpha of 1, which we said. Remember, this yellow line has the alpha of 1. And it has a lambda of 0.3, so that's right here. Why is it a lambda? Let's show this both on the screen at the same time. The lambda right here at the bottom, we'll talk more about what these mean tomorrow, but we're right about here with the yellow line and the lambda of 3 point something right in here. So it's telling us which model to use. And then we're going to look at the results of the best model right here. The best model has an RMSE of 16.08. Now, guess what we can do? We can just go right here and we can get how our model does on the holdout with this code. All the code is right here. Oh, do I not have that package loaded up? Might have to load a package. I put new R on this computer. So since we don't have it, we're going to install packages E1070, E1071. That's right. I was blocking it. Packages installing, library E107, there we go, run that, and post resamples in there, and we get it. Error in table arguments must have same length. Don't like that. I might have to do it by hand. Post resample, square root, let me see here. This will get it too. Okay, I'll figure out what's going on with post resample. That's the RMSE on the holdout. Yeah, RMSE on the holdout manually. That's actually what I thought. One is going on right there. We should, let's hope this works. NAN, oof. What is going on? Why are we getting that? Let's see what's going on here. GLMnet, we do have a GLMnet stored, so that should be all right. Let's see if the predictions are being made. That might be where the error is at. We might not be getting predictions. We are getting predictions. We are getting values. No, we're not having values. Oh, hold out Y. That's what it was. It's always something small. And there we go. There we go. So this is just the manual version of it. And you get an R squared. Beautiful. So if you want to know your R squared, there it is. And you can look at your R squared of your best tune. This is what's amazing about this type of code right here, is you can go here and you can get your R squared. So you could compare the R squared if you want. But we got the RMSE here. And since this is a list, so this is this list right here. 1, 2, 3, 4. So let's go here and go row 1, column 4. There we go. That's the nope, that's the R squared, so it's 3. So that's the RMSE. Let's call this, this is RMSE on the train, basically. And we're going to go right here. And I'm going to use the train for just a moment, because we could get, is that the validation? Let me think for a second. No, that is the validation. It is giving us the validation. So this does give us the validation. It's not on the training data. It's how it worked on the validation, because that's what it gives via these estimates. And then right here, this right here, let's look at the output from this. We want the second one. I think that's a named vector. So since, no, we want the first one. Yep, that's the RMSE. We're just going to call this RMSE holdout. And let's change it, RMSE holdout. And now we're going to look at how these look. We're going to take the RMSE holdout and do it over the RMSE validation. And yes. Why am I happy? Why am I very happy about this? Why am I very happy about this? It's literally everything we've been covering today. Why was I like, yes. And why is it good? Not overfit, exactly. I just confirmed it's not overfit. That's something we were covering below 10%. Exactly. And you know what's interesting? Do we still have that other ridiculous model up from earlier? I don't know if we have too much output to go find it. Our model typically misses the predictions of somebody's weight by about 16 pounds. And then when we tried it on new data, it missed by about 17.5 pounds. So our model typically missed by about 16. And then on new data, it missed by about 17.5, which is pretty close. But if we look back to our original data, which is up here somewhere, I think I'm about to get to it. When we look back to our data all the way back here, our best models, this was our best model right here. Our best models in here were doing about 14. This model here that someone might say to, wait a minute, you just made a model earlier, Brian, that missed by about 14. But here's the thing. The model here that we had that missed by 14, so missed by 14 on the data it was made from, missed by 36 on new data. But now, down here, for the new models we just made via data mining, we have misses by about 16 and misses by about 17.5 on new data. So yes, this data right here was so insanely overfit. And even more so, let's put the naive in here. Really good notes from today. I need to drop these in because this is the whole theme of tomorrow. This one was like 37 and 37. And let's go here and say naive. So this was the naive model. So the naive model is right here. That was the naive model. And then this was all squared. And so that's the all squared model. And this was data mining. And it was so quick to do. If you notice, we had all the code set up. And we'll be going through these models tomorrow and interpretations of them. But if you see the differences between these, the naive has such high what? This is now a review. So we'll be doing this lecture tomorrow, but this is a review now. The naive has such high what? The naive, when you look at this right here, has such high what? The naive is so ridiculous on this. Has such ridiculous what? What is the naive really bad on? Bias. It's so bad. It does horrible. But hey, it's got low variance. I mean, it does about the same on new data as we would expect. It's got such high bias. It's just horrible at making predictions. Hey, this one's great at making predictions. This one is super accurate from the data it was made from. But when you try it out on new data, it falls apart because it's so dependent on the data. But this one right here is where we hit that middle ground. This model right here is what we were showing off of where we get to this perfect middle ground. Here's your naive. Here's that great model we found. And then here's the overfit model. Because the overfit model is going to have such low bias because you're throwing in so many variables. And here's that really great model we just found. And there's other techniques we could do, but this was one technique. The technique I did is called elastic net regression. It's a combination of lasso and ridge regression, which kind of optimize. I'll show it in the last 2 minutes. I'll just show you the slides on it. So where is it? Regularized regression right here. We'll go through this tomorrow. We'll do these notes. But with the regularized regression, the goal of it is not just to reduce this, which is the bias, because that's basically it's sums of squared error, so it's related to RMSE. That's RMSE's best friend. It's basically the same thing. But the goal is to get very small whats, not just to get small bias, and this is the variance component over here, but the variance component focuses on getting very small or very few, starts with a C, last bonus question of the day. The variance component focuses on getting very few or very small what's for your model, which is your boom, initial right there. You got it. That's it. Very small coefficients, which is extracting the information. Because if you have big coefficients, you're extracting more information from your x's. So we're putting in a penalty in these models for the coefficients. This is the bias. It's just how much your model misses by. This is the variance. And this right here is how much we weight the variance. That is the lambda by saying how much the variance will be weighted. And then the alpha is how much we do the lasso or the ridge. This right here, since it's the squared, is the ridge. It's r squared. It's not related to r squared. It's how I memorized it. It's squared, so it's r, so it's ridge. And then lasso is absolute value. So this is lasso right here. That's ridge. That's lasso. Don't worry about which. It's just the more alpha goes from 0 to 1, which is a ratio to your alpha to ridge. So when alpha is equal to 1, it's basically all lasso. Because you can see right here, if you put a 1 right here, it's all this. And then be 1 minus this. And then you take this quantity right here and you do like half of it. So you do, yeah. So that's what we got going on. That's the end of lecture today. We got a peek into the future. We'll be doing these slides tomorrow. We should finish them. But it's all about knowing how to do regression. Thank you so much. Yeah, we did some really powerful stuff today. And we also got to see a really cool model that was so easy to do. And you could predict something else. You could predict height right here. And, it'll do it instantaneously. And it'll tell you your models. And then we can see about how much we're off when predicting height. I love these graphics, if you can't tell. They're so cool. And we just made, how many models did we just make? Oh, man, look at the relationship with that. I mean, I might even make this finer. Watch this. You want to see something awesome? We're going to do something awesome in class. I mean, we're over right now. But I'm going to change this to 0.01. This might take a moment. Oh, wait, no, I don't want to do that. Well, sure, why not? I'm going to change this to this, and this is a bad idea. Do we stand a chance? Well, no, good question. So this is going to take a moment. Did I already say that in this class? I don't know if I said this to you, Ahmed. I can't remember if it was last semester or this semester, but when it comes to Kaggle, which is awesome, look at this. When it comes to Kaggle, the package we're using right here, because I made my grid so fine, we can see like all the models in here are virtually identical. I mean, the RMSEs we're missing people's heights typically by about 2.73 inches. All these models are probably virtually identical. They're all about the same model. The models get very different as you go out here, and these are like worse choices of models. The reason that I don't know if we can win Kaggles, which I hate to say that, I'm so sorry, is because the guy, did I already tell you this? Zach Mayer, I think his name is. Let me pull him up right here. Zach Mayer, Data Robot. There's Data Robot. Oh, cool. Wow, I've never seen their visual AI. Okay, maybe I should look into that. Zach Dean Mayer. It's with an A. I misspelled it. This gentleman right here, I'm about to show you, he is, he's a guy, vice president of data science and he's a Kaggle grandmaster. This guy created the Carrot package. He is one of the co-authors of the Carrot package, which is Carrot on this page. Let's Control F right here. Carrot. Carrot's not on there, but this gentleman right here is one of the co-authors of Carrot. So we're competing sometimes on Kaggle with a guy who made the package we're using. So I'm not saying we can't win, but sometimes on these sites we're competing with the people who makes the tools we're using. So and that's why he's a grandmaster, because he made the things we use. So you might be able to beat him, and if you beat him, he'll be like, "How'd you beat me? What'd you do? How'd you use the tools I made?" But Zach Dean Mayer right here designed, and I'll look at the question. I see a question in the chat here. So Carrot, Zach Mayer GitHub. He made Carrot Ensemble too, which is even bigger. He's got his data profile right there. But here he is again. Carrot Ensemble, Carrot. Forecast. Did he work on the forecast package? This he's unstoppable. Zach is a data scientist, a data robot, and co-author of the Carrot package in R. He's fascinated by predicting the future and spends his free time competing in predictive modeling competition. He's currently in the top 500 data scientists on Kaggle, and took 9th place in the Heritage Prize as part of the Analytics Inside team. So, yeah, he's tough competition. I'd really love to meet and talk to these people, but we might be able to win. But just remember, especially when it comes to Kaggle. And that's why, here's the really good thing. If you want to get more competitive, look into maybe getting your master's in business analytics. Also, learning more packages on your own, like learning dplyr, which is more data manipulation, but still good to have. Learn the forecast package. Learn Carrot Ensemble, which we briefly touch on in this class, but learn how to visualize data. The more you learn about data, the better you are. But Zach's been at this for he's probably been at this for 15, 20 years, and he designs the packages. We will win as a class. Well, that's the thing, is like one Zach is worth a ton, because, I mean, you give one Zach one supercomputer, and he could just like destroy us. It says AVIS not found. Let me look at this, Caroline. Good question. Is AVIS not available? I might have to send out an announcement and say, don't worry about it, because if AVIS was like taken down. So let's see right here, Caroline. Thank you for posting that, Caroline. Sorry, I took me right there. Could you help me with 1C and 1D on homework 6? Yeah, let's take a look at that. Let's take a look at that. Let's think. I don't think I have any meetings today. Do I have meetings? Let me look at my schedule. Let me look at the schedule. Google Calendar. Don't know when Google Calendar. Yeah, we hired Zach to do the Kaggle, so I don't have enough space. Ah! Okay. We hire Zach right here. Yeah, Zach is, I mean, that's why he's really good at what he does. I'm always impressed, and I need to compete in a Kaggle again. Maybe I'll do that in July. Maybe in July I'll take another try at a Kaggle. I don't even know, is my profile on there? Did I do it? Okay, wait. This is homework 6 or 7. On homework 6, A rules. Wait, what? Sorry, brain's booting up. Viz. What? We should do a web. What is CTF? What is that? Am I going crazy here, Caroline? Why am I not finding it? And let's just try installing A rules viz. Let's try installing A rules viz. A rules viz. Once again, I redo computers all the time. Oh, it's getting it. Yeah, it's got it. Okay, Caroline, run this line of code right here. I don't know if there was a typo. Install packages, A rules. Oh, you might have it in a single quote. It might not like that. It might be mad about the single quote. Is it? Oh, sorry. Yeah, I've got typos. Yeah, I'm very sorry. This is what happens when I try to change things. Association rules, right? Or no, association rules. Okay, association rules. Yeah, is this right? Yeah, sorry about that. Mass confusion. Oh, and I didn't change the don't. Yeah, it's do viz A rules viz. So this should load up now. We should be able to load up this. We should be able to load up this. That's looking good. Okay, we're good. Is it working for you now? It's on homework. So does this work now after you have the install right there? And then I'll look at the next question. And we got 1C and 1D for 474. Thank you, Jordan, for always putting the things right there for letting me know. Does it work now, or what error are you getting? Because you should, with this code I put in the chat. Got it. Awesome. I think it was the single quotes. Great job, Caroline. Thank you so much. 100 off-star points right there. Thank you for hanging out, asking the questions. And Jordan was wondering about I think it was 1C and 1D. Okay, let's look at 1C and 1D. So 1C and 1D. Let's go to 1C and 1D. Here we go. Build a rule set using the support of this and a minimum level of confidence of this. Do not put any restrictions on the lengths of the rules. Okay, that means we don't care about the length of the rules. They don't need a min or max length. Remove the redundant rules and non-significant ones. There should be 19,981 rules left. Then print out the top 10 rules in terms of lift to the screen. Okay, so what we have to do right here is we have to use the a priori learning method. We also have to make sure we have our data set read in. So we need the music data set. Let's make sure we have that downloaded. So we're going to make sure we have music data set downloaded, which we're going to use as a transaction. It's called music likes mods. Is this? So it's music likes mod. Did we rename it? Okay, good. There it is right there. And let's download the grocery because we might be using that. Okay. We got our data sets downloaded. And I don't think I'm in my right working directory. So I'm going to set my working directory over to downloads because this computer. And we open. So now we're in the downloads right here. We're going to read this in. It read in. That's awesome. We're going to look at just the top people's preferences when it comes to music. So this is going to show us the top preferences right here. We got the Killers on there. Awesome. And Pink and Lady Gaga is a little bit dated. We could look at the top 10. We'll be able to see the names better. We got Paramore. They're still around, but I don't. Lady Gaga, there we go. Britney Spears, it's definitely dated. It's just not as big now. The Beatles, Katy Perry, Rihanna, Madonna, Christina Aguilera, Avril Lavigne, Radiohead, Paramore. So you can definitely tell that this is not the most recent of data sets on people's playlists. So does that make sense what's going on right here? You're giving clues. Oh, cool. I like that right there. Oh, yeah, CFT. I should know that from all the games I play online. Capture the flag. Good stuff right there. I like King of the Hill. King of the Hill is my favorite when it comes to games where you have team games. I don't know, if Fortnite has King of the Hill, probably no one plays it. It's probably like an option, but no one plays it. I'd be like, I want to play that. So we'll go down to, I think it was C, where we have to make the rules. Now, the quickest way to do this is going to be to go to the notes, because we're going to just kind of take the format and we'll review what it says. Let's go to open, and we want to go to association rules. There we go. Okay, so we're going to Google the a priori. So we're going to go to a priori, most powerful search. Thank you. A priori. A priori. What? What? Am I losing my mind today? And finding rules. Wait, here we go. It doesn't have a double P. Cool. Here's the a priori learning method. Let's go grab it. And let's take a look. So we're going to go into here, and we have to run the a priori learning method. Let's break down what the a priori learning method has and adjust it for our preferences. Yeah, we'll do that. This is going to sub-indent right here because we're inside of this. If you notice, it said there is no minimum length. Let's fix this to look like that. And now we have something that looks nice and neat. We're almost there. We just have music is our data frame we're using. So music is what we're going to make the rules from. The parameter right here is we want a support of the following. Guess what we can do? We can take this support right here and just drop it right there. Does that make sense what I did right there? I think it was Jordan was asking. It said, hey, have a support of at least this. So I just took it and dropped it in. What are the additional changes I need to make? Help me out here. I need to make 3 more changes to this code. What other changes do I need to make to this code to get it to work the way this wants me to make it work? And you can practice just writing this out. I copy it. I don't know. I'm like, it exists. I'm just going to copy it. And then I think it helps to see the structure of it. So you can see like, okay, we're going to make rules from music. Here's our parameters on the ways we're doing this. And this is on your guys' final. Then, so this is just for Dennis. We're running for 474. We're going to figure out associations between the way people like certain artists. So the whole goal of this code right here. Oh, but this isn't fixed yet. You're right, Jordan. We'll do that next. But we haven't finalized the way that this a priori learning method is going to work. Because support is the amount of time a rule applies to a group. We want rules to apply to at least 80 out of 1,821. And then confidence is the percent of confidence we will have in someone liking the right-hand side given the left-hand side is true. It's the percent confidence in the right-hand side if the left-hand side is true. It's the probability of the right-hand side. So we're saying we're this confident they will like this given they like these artists or artists. So what else needs to be changed right here? After we'll remove redundant and all that stuff in a moment, but what else needs to be changed? Hint. Hint, hint, hint. I think I got this one. And then also, we don't want these right here. We're not going to use these. And this will remove right here. Now, this comma right here starts the next argument that is control list within the a priori. List was a sub-argument. That's why I like to sub-indent. So list ends right there, and that's another argument. 4 and 5b? Yeah, we'll do that next year. We got that. You got it, Caroline. Remind me if I don't. I should go to it next, but I'll go to it. And now we should get the rules. We got the rules. And now we need to remove the redundant and the not significant. That's also in the notes right here. Let's go make sure it is. And let's control F, redundant. There it is, redundant one time. And wait, is it not in here? Be cautious of redundant rules. I swear it's in the notes. Don't tell me we took it out. It is in the activity. Did we take it out? Simplified rules, control list. That's not doing it. So we reduced the notes some semesters, and it is in the activity for this. I might have to send a reminder, be like, hey, this is how you remove redundant rules. Yeah, it looks like I'm going to send out a reminder because I don't want people to be lost on this. Yep. Why is that taken out? It's is.redundant. I can probably write it myself, but you see if rules are redundant. So you go here and you go is.redundant. And you look to, that's music. Why am I doing music? You go to rules. You see if rules are redundant. Yeah, no, I understand. It's not. So this is telling us if a rule is redundant. And so is.redundant just sees if a rule is redundant. So what do we want to do? We want to go to our rules. This should do it. I'm just trying to think through it myself. And we want to go to our rules. We want to remove from the rules that are redundant. Cool. And we're going to overwrite the rules with these rules. And now we should be able to remove, we only want the is.significant rules. And I think this will work right here. And now let's see how many rules there are. 46403, which is not the right amount of rules. We have too many rules. Let me see here. Remove the redundant and non-significant ones. There should only be, so rules is significant. So these right here, I think the change, when did the change not happen here? Let me double check. Rules, and now we've removed out the ones that are redundant. Let me look at the rules as we go through this. Rules, was that not overwriting it? Rules right here should remove out the rules that are, there's only one redundant rule? No, I saw it visually. I saw it visually that there was not one redundant rule. Is.redundant, it should get, oh, you know what? That's gonna, let me double check. Might have to look at the notes real quick on this. Let's see if this does it. There we go. There we go. Look at that. We want to remove the positions of them, so it's the positions. I knew something was off. Just got to work with the code a little bit. That's why we got sanity checks. And I think they're all significant. So we only want the ones that are significant. So if I do this, this will actually, the code right now should destroy it. It should, I guess, should get 0 rules. Yep, good. That's what I wanted to see. We don't want to remove the ones that are significant. We want to keep them. So now we get the right amount of rules. Does this, let me drop it in the chat. Here's the code. Let's just send this out in an email now. I'm going to send this out real quick and say, help for 1C. Great question right there. That's why we have office hours. Okay, help for 1C. Help for 1C. Here's how to reduce the rules by removing redundants and only keeping significant. I was like, well, look it up when we can figure it out here. Removing redundant and only keeping significant. Okay, so that should be sent out now. Everyone's got that. I like to give hints and like to give answers in office hours, but if I don't want people to spend an hour coding that. But does this make sense, Jordan, what's going on here with 1C? Like how I'm able to say, go to the positions in the rules that are redundant. So this code right here checks to see if a rule is redundant. I get those positions. I remove those positions from the rules, and I overwrite rules with this right here. Then this code right here sees if a rule is significant. I go to the positions of the rules that are significant. I only keep those positions in rules, and I overwrite the rules. Now, everything was significant, so rules are usually significant, especially with this high of confidence and this the lift values we put in. We're just getting significant rules anyway, so that didn't change the set. That's why I knew removing the significant would bring it to 0 rules, because I was like, I think they're all. Yeah, I know. Sorry, we reduced the notes, and sorry, I feel really bad about that. That's why I immediately sent that out, because if you go to the activity, which I didn't do much, we didn't do any of the activity yet. If you go to the activity, you would see these in there, but they should be in the notes, and we reduced the notes, and because we had issues where if you look at the reviews, people would say things like they fly through the notes. So the notes used to have like 120 slides, and now some of them have like 60 or 70. But there's so many little nuanced things that, there's so many things. So we realized this class is pretty jam-packed, and I'm probably going to redo the notes again between this semester and next, because we just redid them last semester, and I don't like them. Sorry, I don't like the notes. Then print to the screen the top 10 rules in terms of lift. So here, I'm going to try to do it myself. You ready? Okay, let's do it. So when you do inspect, if you remember, inspect immediately returns the output. So you have to be careful. If you go to inspect rules, you can't inspect the rules and then take from this. Probably bad idea. Exactly. Oh, that was a bad idea. I said it was a bad idea, and then I did it. Stop. And so this is a bad idea too. You think, oh, I'll just go here. I'm going to get the top 10 rules. Oh, there we go. Oh, and it's just doing the same thing. I said top 10. No. Stop. When you run inspect, you keep getting 0 rules. Double check, take the code I have right here and do it in steps, Caroline. You might want to post your code in the chat and I'll double check. But do it all in steps. Pause the screen on this. Make sure you have it this way. And every time you make this, check what you have. Be like, okay, I have this many rules. Okay, I have this many rules. Check what you have each step of the way to make sure that each step of the way you have the right amount of rules by the end. But so start with the first one where you make it. And if that makes the right amount of rules, then check it again. And here's the numbers you should see. You should see it go from that number to immediately that number. And the last one, since they're all significant, it doesn't change it. So double check each step of the way with the amount of rules you're getting to make sure it's going down each time and starting with the right numbers. Great job, Caroline. Great job. And so what you need to do is we got to sort these rules. And so we should go to sort the rules. Remove this. And we're going to sort the rules. And now we're inside of the sort. And we should just get by equals confidence. Does it say confidence? Yeah, we'll see what it said in a moment here. Oh, don't do that. And go here. I'm only going to look at the top 5. Why not? I could have looked at more. Let's see if it did it right. Let's see if it did it. Because I think that wrapped the screen. That's graphical error, as always. Oh, really? They added this extra column, and there we go. Okay. Is this sorted? Yes. This is sorted by confidence. And I don't know if it wanted confidence. What did it want it sorted by? By lift. Yeah, there we go. These are the top 5. It wants top 10. Really? Really? Because it's so long now, you get these. But these are the top 10, and it's 1, 2, 3, 4, 5. 5 is the one that I want. Like -5. Oh, it doesn't like that. Dang it! I can't remove that out. Oh, because I know. Yeah, that's why it does it. Well, that's a bummer. Oh, we can zoom out. Or is that? No. This is fine. It's just how long it is. Okay, cool. This is the output right here for the top 5. And if you look, what does this confidence right here mean? And is it sorted by confidence? Did I misspell confidence? Because it's not sorted by confidence right now. Oh, it's sorted by lift. I did sort it by lift. Here's the lift for this one. Lift. So we have this right here. How are you looking on this, Jordan? Pretty good. Got this worked out. Is it showing you there's 83 people this rule applies to? And if you think, remember, we set our a priori learning method to make sure that we had at least 80. The support right here needs to be at least 80. And you notice that these are the support numbers, which should be at least, if we look at this equation right here, this applies to at least 4.3% of the people on the list. Yep. And so now you see these numbers are related. Like if you take this number right here and divide it by 1821, you'll get this number right here. So do you understand that this number right here is related to the percent of people who have Britney Spears, Kylie Minogue, Mariah Carey, Rihanna, and Jennifer Lopez in their playlist. This is the percent of people who have all 5 of these artists. And given that people have these 4 artists, the probability that they will have Jennifer Lopez is 70%. But you know what I can figure out pretty quickly? And this is for the final. This is where it gets tough because there's a lot of topics. I can figure out the probability that somebody listens to Jennifer Lopez. And I can tell you off the top of my head, it's about between 9 and 10%, maybe 9.8%. How did I figure out that the probability somebody listens to Jennifer Lopez is about 9.8%? How did I figure that out off the top of my head? This is the confidence. Boom, Jordan, you got it if you know that. Pretty easy. You just divide the confidence by the lift to get the original probability. So what you can do is you can go to item frequency. This goes to other questions in this. And you go to item frequency of music, because you're going to look at the item frequency, and we're going to take Jennifer Lopez's name spelled exactly the way it is, and we're going to go to the position of Jennifer Lopez right here, and whoops, got to put in quotes, quote, 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 and it's 9.8. 9.8. It was pretty easy because it was basically 70 divided by 7, which is 10, but this is a little bit bigger, so it's going to be a little bit less than 10. So that's what I was doing in my head right there, is I was saying, oh, what is the original probability of Jennifer Lopez? Well, it's going to be her current probability, which is the confidence for given people like this, divided by the lift to find the original support or item frequency. So item frequency of Jennifer Lopez is the support of Jennifer Lopez. Is that making sense right here? Is that making sense? Hopefully that's making sense. You can figure out the probability that somebody likes 2 artists, and we can see the code for this. We'll go right here. Let's just hop over here to look at it again, and then we'll jump to Caroline's questions too. You can do %AIN. If you look right here, we can just do a subset. So you could subset the items right here. So items, %IN%. I always forget that it needs to be items. I think it should be all right. G is the transaction data frame, and items, yeah. So if you want to figure out that somebody likes Jennifer Lopez and a certain artist, which you could do, and we should, here, we'll do this long problem right here to figure out exactly what we just figured out. So we're going to take our transaction data frame, which is music, and we're just going to do a quick test right here. We're only going to have Jennifer Lopez right here. So we're going to put Jennifer Lopez right there, and we're going to run this. And now if we go to sub, it's right here, 2,000, let me think here, 2,400, it's 180 transactions. Is that how many? Yeah, 180 people out of, let's try this, 180, no, wait, something's off. 180, is that right? Yeah, it is about right, because there's a total of how many transactions? How long is music? Music has this many. There we go, okay. So if you do this right here, you can figure out the percent of time Jennifer Lopez appears, which is the exact same number. That's a really long way of doing it. So we could have just also divided by, we could have taken this right here. We could have taken our sub, or we could take, can we do sub divided by length of music? What does that turn out? Yeah, it doesn't like that. Sub, can we do length of sub? That might work. Yep, that did it, because sub has that many items in it. So that is, there's total of 180 playlists, and there's 2,459 possible things like artists. So I believe that the earlier question wants to do, yeah. So you can take and you could figure out the probability somebody likes. Like here is the code right here. So this code right here on the screen right now, you can change, and you could say Jennifer Lopez and Ben Folds 5. Oh, I think it doesn't have spaces. This thing doesn't have spaces. Ben Folds 5. And now nobody likes Jennifer Lopez and Ben Folds 5. Does anyone like Ben Folds 5? 7 people like Ben Folds 5. Woo! Is it Ben Folds in here? He's been in Ben Folds, just Ben Folds, for a long time now. So Ben Folds 5. Maybe they just know him as Ben Folds. 12 people like Ben Folds. And then you could say right here, you could do people liking Ben Folds and Ben Folds 5. So now here's the people who like Ben Folds and Ben Folds 5. 6 people, which is good. That means, these 7 people, only one of them doesn't like Ben Folds. So you can do this right here. So yeah, that's there. And I think if we do OIN, will we get 18 if we do OIN? Get 0. We do PIN? I think PIN should get us 18. Don't worry, those are not warning message, sure. 13. I always forget how PIN would partial match these. Let me try one thing here. Let me try PIN with Ben. We'll do a partial match on that. It looks to be doing a partial match on the name. Yeah, it's doing a partial match. That's what PIN does? I finally learned what PIN does. PIN looks to do a partial match on the name, so you can search. What did I do? Whoops, let's just exit out of this and do 2. There we go. This is all people who like artist B. Yeah. With a B in their name somewhere. Never heard of Ben Folds? Greatest pianist of all time, Ben Folds 5. Ben Folds. Mr. Ben Folds 5. See, if you didn't know how to spell a name, you could say it like here, Brian. Things with the name Brian in it. 36. So we could look, hey, let's look at this. Let's look at this. So these are the, we can look at the sub. So I think we go to inspect, right? Inspect sub. Here we go. Brian Eno. Brian Eno. Who's Brian Eno? The Brian, Jonestown, Mass. I think I've heard that one. Another Brian right here. Brian Littrell. Any other Brians? Where's the Brian in this one? Brian. At those Brian Spears. So the PIN is a partial match, which is awesome. I'm learning things right here. But you can do a lot of cool things with this. So you could search, like, if you were to search, like, Emperor, you would get this band right here. And you could probably do a partial match on it. So you could do a partial match with the PIN right here and put Emperor. And now you've got all the bands that have that or another thing. So PIN is a partial match. I should learn more specifically what OIN does, but you can partial match stuff like destroy you. This will destroy you. So funny. So you could do destroy and you get all the bands that have the word destroy in it. And I don't think it cares about upper or lowercase. I don't think it does. Come on, computer. And here, let's check this. I don't think it's case sensitive. Ooh, it is case sensitive. And there might be a thing to change it so it's not case sensitive. So is this making sense for all these? We're going to hop to Caroline's question. Let me see what the next one was, because you said D also. You should have found that the top rules of Lyft are this right here, Hillary Duff. Let's double check our rules. Is it the top rule is Hillary Duff, Rihanna, Ashley Tisdale? Ooh, wait a minute. Hillary Duff, Rihanna, Ashley Tisdale. You should find that one of the top rules, it's not the top rule, it's one of the top rules. And look at that. We got the confirmation. We did it. 81 listeners. There's the 81. Like this set of 3 artists. First, explain how you get the number 81 for the support. What's the support mean right here? We were coming this moment ago. I'll vanish. What's this support mean right here? This is the support of the rule. What does this mean in words? If you were to tell someone exactly what this mean, what does that mean right there? What does that mean? 81 people, what? You can put the answer in the chat. What does it mean for these 81 people? Of the music list we have, 81, yep, that's it. 81 people listen to all 3. The support of a rule is the amount of time the rule applies to everything. Like the 81 people listen to Hillary Duff, Rihanna, Ashley Tisdale. Like they have all 3 of those in their playlist. First, explain how you get the number 81. Cool. Second, write a line of code that produces the 81 by counting up the number of transactions that contain all 3 items. Guess what? We were just doing that. We got this. So let's go here and grab our code that we were doing. Not that one, 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 not that one. There we go. This line of code right here is going to take, and sure, we can subset the music. That's fine. And we're going to grab Hillary Duff right here. There we go. Boom. We're going to take Rihanna right here. And then we're going to put a comma, and we're going to go Ashley Tisdale. We're going to drop this, and we're going to run the sub, and there we go. So we're asking for a subset of people who have all these items in their list. So we're going to make a subset of all of these items right here, and they must have all of these items. So this confirms that they have all these items. Now, what is this? What does that code do? Which PIN is probably going to turn the same result. Was it mad? Oh, you can only use 1 for PIN. Oh, that's interesting. Partial match only likes 1. So what is this going to do right here? What is IN going to do? IN will be people's music lists who have any of these artists. They could have all three. They could have two, but they have to have at least one. So their music has one of these elements in there. And so we look at this, and of the people who have one of those elements, there's 484, like any of them. Yeah. And then OIN, I'll have to read more on OIN. I can't remember what OIN does. 0. So, oh, it's only, that's what OIN is. It's so OIN is you can only listen to that one artist. So you would only listen to these artists. Like if this right here, this is someone who only listens to Hilary Duff. That's the only artist they have, which we got 0. So OIN is only, you don't have to know these ones. Rihanna, I mean, Rihanna's more popular than Hilary Duff maybe at this time period. So let's see. 0. Yeah, it's really hard. What is it? The Beatles. Let's go IN. Am I spelling it correctly? Who's more popular than the Beatles? U2? Like, I want someone to only listen to one band. Oh, Item Frequency. What was it? Yeah, I don't know. Radiohead? Am I spelling it correctly? Cool. OIN. And nope. I mean, we could probably search for people who only have one artist and stuff, but we're trying to find people who only have these items. So, yeah, we could take a look at the data frame. But does this make sense what's going on here, Jordan? Do you understand how these codes work? We don't use OIN in this class, and if you're looking for like only a certain item or only a certain thing, nice job, Andrew. Congratulations. Great job. Yeah. That's up there. The average right now on the test looks to be in the low 80s, and that's an A. You have at least an A right now. Yep, cool. And then Caroline was asking some questions. Let's hop to Caroline's questions. Sorry, Caroline, we did a lot of fun like OIN, PIN, which I actually learned what PIN means because I've been doing more partial match stuff via strings. So it partially matches a string, which means it just looks to see if it's anywhere in the string. And then there might be like a case-sensitive thing. Probably... I don't think this will run. There's a way to look at the notation on it. I forget how to look at it. It's in the A rules package, so it's going to be under... Oh, you know what we need to do? Real quick, we're just going to take a look at this. A rules. There it is. Can we look at you? See, there's the AIN, PIN, and why won't you show me how this works? Yeah, it's a function. I guess it does stuff. That's what it does. So, yep, 4 and 5B. 4 and 5B. Brian, I said when accidentally. Wait, I'm so confused. I don't know what that means, Andrew. I don't know what that means. Okay, we got some grocery basket data right here. Read this in. This is discussed from New Zealand. This is the ones we're looking at in class. Read in the data. See the R file that accompanies the lecture. Make a rule set of each rule has at least this. So Caroline, Andrew, Jordan, what are we going to do immediately now? Since it says we need to make a transaction data set that has this confidence, has at least this many transactions, and a maximum length of this right here, and then we're printing the screen a certain amount of rules. So what learning method are we going to do? I lean back in my chair. What learning method are we going to do? A priori, you got it. What we're going to do is we're going to go back up here. We're going to grab this a priori learning method. I think we want to remove all the redundance. I don't know. We're going to take this code. We're going to go down here, number 4. We're going to drop the code in after this because we read it in. Oh, it's G. Let's just change that to G. We're going to read this. It runs. We like that. Graphical error. I want to throw big points out. I was starting to read a question and said when. Oh, that's a 0. I'm just kidding, Andrew. You were like, when? I see like this. It's like, you're fine. Oh, wait. Oh, no. I didn't do it right. We want there to be at least 25. So if you want at least 25, let me look at the data frame. So what I want to do is I want to look at the G, and there's 935 things here. So I want at least 25. Does that make sense why I did that right there? I looked at how many transactions there were. There's 169 items that people are buying, but there's 9,835 carts. You could look at it in the global environment too. But with the 9,835 carts, we want there to be at least 25 carts that this applies to. So the rule has to apply to at least 25 carts. That's the minimum support right there. And then we want to change the minimum confidence right here to 0.77. And this is just how we're creating our rules. Now we need to add in one more. Yep, here we go. And we need to do max length. Is it max length? I think it is. Well, we'll find out the hard way. We'll see if it's max length. Yeah, it didn't like that. It is properly spelled. It's probably spelled max length. Max length. There we go. Can't remember the name of the argument. So many arguments to remember. And then we go here, then we go here, then we go here. 0 rules. No. What did we do? Okay, let's see. Did this create 8 rules? We shouldn't be getting 8 rules. So we see right here we need a confidence of 77. The rule applies. Let's max length of 4. Make a rule set so that each rule has at least a confidence of 0.77. Each rule applies to 25 transactions. And the maximum number of items in the antecedent. Oh. Do you see it? Do you see it? That. The maximum, and that have a maximum of 4 items in the antecedent. There's a trick, and I got tricked. It says the antecedent. What 2 parts of a rule are there? What 2 parts of a rule are there? There's the antecedent, and for 100 points, there's the what? The 2 parts to the rule are the antecedent and the 100 points, who knows? You got the antecedent on the left-hand side, and you get the we'll see in the notes. I do know it, I promise you. Hopefully someone says it in chat. It's the antecedent and the consequent. And the antecedent and the consequent, if you add those up, you get the length of the rule. So your rule has an antecedent, and the antecedent is the first part. We should see your antecedent and consequent somewhere. There's the antecedent, and there's the consequent. And so here's your antecedent. It's what starts the rule, and here's your consequent. It's what ends the rule. So the min rule, the max length shouldn't be 4 because it says the antecedent. The max length should be 5 right here. That's tricky. Let's go ahead and just take a look at these rules. We should have more rules. We have 9 rules. It doesn't say remove the redundant, but you would think, did we make a mistake on these? Is dot redundant? So none of the rules are significant? I think that's where the problem's happening, because I bet the redundant's fine. None of the rules are statistic. Ooh. Wait, all the rules are redundant? Rules which are not redundant. What is going on right here? Is redundant on the rules. So it should narrow down. It should only keep the rules. Set of 0 rules. The positions of the rules that are redundant, not redundant. Because this should be all trues now. Integer 0. Hopefully. The code ascent worked. We got the code working. It's 9 rules, and I think it says we need 9 rules. I wonder why it's having such a problem right here. Which... So this is running the is.redundant on the rules. That's trues and falses. Oh! Wow. That's interesting. So... The issue is as follows, and I didn't know this would happen. No wonder it doesn't tell us to run this. What is this returning? It's returning nothing. It's not evaluating any... Wait, but then it should turn that to trues. Oh, so wait. Let's try that. Let me see what this applies to. Is redundant, true. And those are all trues now. Well, there's always an error with the code, right? On the which is not logical. So it's turning the is.redundants are currently falses. Oh my gosh, Brian, your brain's not working today. There we go. Might. The code worked. That works. That works. That works. That works. That works. Okay. There we go. Yeah, that's the problem is you have a code that works one way and won't work another. I just didn't flip my trues and falses. And now we got 9 rules. Was it 9 rules? Wait, print to screen the 7 rules that involve at least one dairy item, milk, butter, milk, butter, are these right here. So this is super nice. So Caroline, what do I want to use from before to make these rules? I'm going to make a subset. I'm going to go sub, and we should be able to do sub, is it items, percent, in percent, that, and I think I've done it. Unexpected, right here, concatenate. That's where I was missing concatenate. Unexpected item X, what's going on? Still mad about it. Let's go and get that. I see Andrew has a question, 2 seconds. Oh, it needs the data frame, that's what it needs. It's the way you have to go here to the rules. And so wait a minute. We got the rules. We should be able to subset the rules. Let me see. I don't subset, the way you have to subset rules, and that's the conditions. So we should be able to subset the rules by the conditions. So subset items of G, that's from the full data set. We want to go to subset. Here we go. Left-hand side, right-hand side, but we should be able to go to items. Oh, because you have to do left-hand side and right-hand side. Cool. Cool. And so I figured out something really cool. So apparently I can have the live chat on full screen in front of you on my TV, but still can't figure out how to type from the remote via voice. Oh, that'd be so crazy. Andrew, figure that out. Because if we were to show people, like, you could sit there in class and actually talk, and you could just, like, talk to me. Oh, that'd be, if it was like on your Google Home, if you're like, I have a question, Brian, how do we do this? And then, like, it would just type it into there. Andrew, that's, like, game-changing right there. So, Andrew, that'd be awesome. Like, please try to figure that out. That'd be amazing. And here's our first condition. We should just be able to go or. Where's my or at? I think this should work. That's not the first condition we want yet, though. Here, we'll call this, let's change this. Let's grab this, and let's make it easier on ourselves and call this milk items. So that's milk items right there. And we want to see that the right-hand side has a milk item in it. And let me look at what exactly it wanted. And let's just make sure this runs for the moment. So rules on the right-hand side that have a milk item in it. 6 rules. And then I think we also need the left-hand side. So print to the screen the 7 items that involve at least one dairy item in the antecedent or the consequent. So we're going to say here, or... Where's my, I almost forgot the or's at. And then, or they can have, because this is the subset. We're inside of subset right here, so we're doing conditions. And this should work if we go to here and go left-hand side. And now we go back and we look at 7 rules. Got it. I triple-clicked the function button, but I went into settings to do that. Yeah, tell me more about this. Like, tell me how it's working and get it working. Caroline, does this make sense right here? That it's going to be easier for me to store a vector of milk items and then just refer to it? Like, this right here is this right here. Like, this will run the same way, but it's much easier to just create something called milk items and then just use it like this. So you oftentimes think, how can I make my code work easier than writing it out twice? Well, let's just create the vector of milk items and then say, let's take our rules, which is what we're subsetting. And then you have to do here subset. This is what... Can we not do subset? Let's see what happens if we don't do that, because that's what confuses me about this format. Ooh, did it work? It worked. Well, we're not doing it the way the notes say, because that always confuses me. You have to do subset equals inside of subset, but it worked. Will it always work? I don't know. But it logically makes sense to me the way it looks right here. And if you look, this is condition 1 right here. This is condition 2. You could go to another thing. You're outside of the thing, but you could do another. You could do another. You could say, and we could look at the rules. We'd have to see what the rules have. Inspect. If we actually want to make rules that this is dairy. They've got tropical fruit. So we're going to say, and that's in the left-hand side. So we're going to say or somebody, or no, we'll say and. So now and, so they must have this. The left-hand side has to have contained in it tropical fruit. And we can just put this in quotes. Doesn't need to be in multiple. We might just get one rule right now in the dairy. 7 rules. Everyone's got tropical fruit? Oh, that's interesting. Do they all have tropical fruit? Tropical fruit, tropical fruit, tropical fruit. Where's the tropical fruit? Tropical fruit. I'm concerned about how this is subsetted now. Because this person has yogurt and they don't have tropical fruit. So it's not doing what I wanted, the curd. So let me see right here in my condition. And left-hand side must have tropical fruit. So I wonder why that's not removing that, why we're not holding that condition true. Try this. That's the or. The right-hand side has milk items, and or the left-hand side has this. And 2 rules. Okay, cool. Those are the 2 rules. Maybe you can't. You know what I think? I think what's happening is once you do the left-hand side, you can't do it twice. It looks to be that, because if we go back to this being milk items, I think once it does you can't be like, you can't do it twice. Now we've got the left-hand side and the right. Okay, so now this makes sense because now they both have to have milk items. So you have to have a milk item here on the left-hand side, and you have to have a milk item here on the right-hand side, which this is a pretty big high lift. People buy butter, root vegetable, yogurt, and they're more likely to buy whole milk 3 times the probability of their original probability of buying whole milk. And once again, we should know the original probability of buying whole milk. Very easy test questions if I put these on the test. The lift is behind me right here. You can see it right there. The original probability of buying whole milk is as follows. One of my favorite test questions to ask because you can find this out pretty easily, and it's 25.55. And we're going to go here to item frequency of G, which is the grocery store stuff. And then we're going to put into here whole milk. And we're just going to spell it exactly perfect. Go to the position of whole milk, and we'll see 25.5516. So you should know pretty quickly what lift, confidence, and support is from all this output. So very, very, very important right there that you know every single one of these and what they mean. We don't need to know coverage, but we need to know support, confidence, lift, and count. So count is just the amount of observations. And 5, unfortunately, the size of these 3 quantities measured, I think it was 5, right? Don't have intrinsic, what does that say? Don't have intrinsic importance. Bigger isn't always more interesting. In other words, sometimes a larger confidence is interesting, sometimes it's not. Sometimes a larger lift is interesting, sometimes it's not. It is found that A, B implies C has a confidence of 1 and a support of this. So it's a confidence of 1. Let's put this, okay. Let's go to beans. Let's go to rice. And let's go to milk. Okay. I think this might apply to this example. Let's see what it means. It is found that rule beans, rice implies milk has a confidence of 1 and a support of 0.12. At first glance, this sounds impressive. 12% of carts have bean, rice, and milk in them, and every cart that has beans and rice has milk in the cart. However, think of a scenario where that has 100% confidence and absolutely no practical consequence. So, hint, think about the support of C. What do you think the support of milk is? What does the support of milk mean? So, what is the support of milk and what does it mean? And then what would the lift be? Just think about milk at a grocery store. What do you think is the support of milk? What does support mean? It's the amount of time. Support for an item is item frequency. So it's the amount of time somebody buys the item. So why is this not interesting right here? Why is a confidence of 1 not interesting? Does anyone have any ideas on this? This is a big one. There's very good theory for this. Like, this is like really not an interesting rule. Like, oh, if people buy beans and rice, they will buy milk. It'd be like, well, yeah, because Yeah, and so maybe the original probability of milk is 95%, so the supported milk might be 95. And so this right here, it only raises the original probability. If you look, you can figure out the lift right there. And that's just theory. I like the theory right there, Jordan, 100 points. Thank you so much. Because if we take the new probability and divide it by the original probability, this right here is the lift. The lift is 1.05. And so people are like 5% more likely to buy milk if they buy beans and rice. And what if the original probability of milk is 100%? Then the lift is 1 because everybody buys milk. So you're like, yeah, people who buy beans and rice buy milk. Yeah, and you're like, but if they buy beans and rice, they'll definitely buy milk. You're like, yeah, because pretty much everyone buys milk. Like, and those are, yeah, that doesn't give us anything of significance. Even though we're 100% confident that people who buy beans and rice will buy milk, it's because everyone buys milk. The original, and that's where it says, think about the support of C. The original probability of people buying milk is like 95, 98%. So it's no big deal that now 100% of people buy milk. It's like, yeah, it's like basically what it was. The lift shows right here, if it was 95%, the lift of right around 5% shows that it's virtually identical to what it was. We don't see that big of a factor increase in the probability of somebody buying milk given they have beans and rice. I think that's got it. A lift of 10. At first glance, this sounds impressive. Given that item A is in the cart, the probability that B is in the cart is 10 times higher than the probability had the identities of the items been unknown. However, it is possible that this lift is not statistically significant and that the rules have absolutely no practical consequences. Come up with two scenarios where the lift, and it goes through this equation, so it gives you all this right here to find it. And so you have to use this. I might leave this one for you guys to hear to think about it. Normally, a lift of 1.5 does not get much attention because it's so close to 1. However, think of scenario. These are really good theory questions. So I did the first one, which is really good. But you have to think of scenarios here with like items that are pretty rare or items you would want people to buy. So I think these are really good business analytics questions. So I'm going to leave these last two for everyone to do. Since I explained, you have to put scenarios in there and you have to say like, well, if the third item is milk and everyone's buying milk, then a confidence of 1 is not going to really be impressive because originally the support was 1. Any other last few questions? Who's got questions? Who has questions? Questions. We did so well. So many topics. More questions. I will check out this video, Andrew. I think it is time. I'm going to go eat some lunch. And I'm going to send out reminders like, just a reminder, go take the test. So I'm going to send out reminders, see how people are doing on the test. If you need help, email me. Great job, everyone. Great job, Caroline. Great job, Jordan. Great job, Andrew, and everyone else. I will see everybody later. Bye, everybody.